Mathematics for biologists. And before we start, let me tell you who am I. This is me. And my name is Shomik Roy, and I have qualified these following exams. And right now, I am studying medical biotechnology at IIT Hyderabad. Okay, and this is the link of my LinkedIn profile. You can connect on me. I am very active on LinkedIn. So if you have any doubts or any question or any query regarding anything, you can just pin me on DM me on LinkedIn. I will also provide this link in the group or mail or somewhere, so you can connect with me there. Okay, now let's start. So this is a 2-day webinar, as we all know, and in the first day we will learn about the common units of biology that are normally used, and the logarithmic properties, the mole concepts, and the pH and pK and buffer Henderson-Hasselbalch equation. And we will also learn about the enzyme kinetic graphs and Stokes solution and many more numerical problems. So these are the topics that we are going to cover on the first day. And on the second day, there are many topics like population growth and biostatistics. And under biostatistics, there are a lot of things, a lot of concepts, and a lot of minute numericals that you will learn. And you will also learn about gene mapping. That's the 3-point cross, and I will explain the gene mapping in a very convenient 4-step process to solve any 3-point cross numerical problems. Okay, now let's start with day 1. Voice is also being recorded. Let me check. Yes, the microphone is on. Okay, so starting with basic mathematics for biologists. What we will cover under this is the some basic SI units that we need to know. SI units, like often we hear about micrometer or angstrom or picometer. Even there are few units like femtometer and attometer. We don't know always the relationship of these units with meter. Okay, so in many numericals we are given in the size of a protein is this angstrom, or a biomolecule is this angstrom, and you have to solve some numerical, but we often get stuck in converting that units in meter or something. Okay, so we will look into that. And also the bigger units, that is the gigameter and megameter or tetrameter or tetradalton, megadalton, all these things we will cover. And apart from that, we will also see some basic measurements of biomolecules or proteins that we need to know, like what is the mass of water, or what is the mass of glucose, hemoglobin, insulin. We need to understand, we need to, as a biologist, we should know these things. So we will discuss about that. And then we will discuss very common biological measurements, like what is the protein concentration in cytoplasm, and what is the diameter of nucleus, and then what is the diameter of water, and why knowing these diameters and dimensions are important. This is like the structural some basic glimpse of structural biochemistry, you can say. Okay, so let's start. Okay, so let me start with SI unit commonly used in bioscience. For SI unit, like for any unit, we know that for weight it is gram, or for volume it is liter. So every unit has a base unit, that is meter or liter or Dalton or anything like that. Everything has a base unit. So let me write here the base, and for this I will take the example of meter, that is length. Okay, so the base is meter, and from there if you go to the left or the right, the measurement increases or decreases. So commonly we think that if you are going to the left, the measurement is increasing, and as we are moving to the right, the measurements will decrease. So we know that in every SI unit, the biggest one that we normally use, that is kilo. So here in this case it will be kilometer, right? Kilometer, and after kilo, hecto, deca. Kilo, hecto, deca, meter, then deci, then centi, then millimeter, right? We know this. But the thing is that in biological, any cellular components and everything, the measurement starts after millimeter. Okay, so we need to know about the millimeter or the micrometer or nanometer. So I will start with that only. So what is the relationship with millimeter and the base variant, that is meter. What is this relationship? It is 10 to the power minus 3, that is 1 millimeter equal to 10 to the power minus 3 meter. And how is it denoted? It is denoted by, sorry, I will change the thickness. So yeah, the millimeter is mm. It is very common, m for meter and m for milli. Okay, so after millimeter, what comes is micrometer. I will not write meter every time just to save some time. And micrometer is 10 to the power what? 10 to the power 6. So the concept is, for every jump from millimeter to micro, micro to nano, nano to pico, the every jump is 10 to the power minus 3. This 3 is the magical number, as you will also see in the kilometer area. The decrease is 10 to the power minus 3 for every step. Like from micrometer, if I go to the next one, that is nanometer. Nanometer is, again, the jump is 10 to the power minus 3, that is from 6 it will be 10 to the power minus 3, that is 10 to the power minus 9 meter. Okay, so from nanometer, if we again go to like picometer will be 10 to the power minus, again 9 plus 3, that is 12, 10 to the minus 12. Again the jump is 10 to the minus 3. Again from picometer, okay, so normally you will find that every, like 90% of the numerical will have only the picometer up to the picometer range, but there are few 2 more units that I think you should know, that is femtometer. What is the relationship with femtometer and meter? Again the same thing, the jump is 10 to the power minus 3. So after 12, what comes? If we add 3, that is 10 to the power minus 15 meter. After femtometer, it is attometer, attometer, and again the jump is 10 to the power minus 3, that is 18, right? So from here to here, the jump is 10 to the power minus 3. From here to here, the jump is 10 to the power minus 3. Okay, so what are the symbols that we use to represent this? For attometer, it is very simple, A for atto and M for meter, right? So femtometer, it is F for femto and M for meter. Just remember that these letters are always in smaller case, not the uppercase, always in the smaller case. And I will come to it, why it is in smaller case and not in uppercase. So for picometer, the representation is simple, P for pico, M for meter. And for nanometer, any guess? Obviously it is the same, that is Nm, N for nano and M for meter. For micrometer, we use this symbol, this is micrometer. Now, like it may get confusing, like what is the relationship nanometer and nanometer and meter, or nanometer or micrometer. You cannot just see it in the like exam hall and write this millimeter, micrometer and jump 10 to the minus 3 step, right? So we need something to remember this, like relationship between the meter. So I came up with a mnemonic. As you can see, this girl is sleeping and taking a nap in between her studies. So she is like taking a nap. So the mnemonic is, her name is Millie. Okay, her name is Millie. Suppose her name is Millie, and Millie is taking a micro nap. So Millie took a micro nap. This is the mnemonic. Millie took a micro nap. So let me explain the mnemonic. What is Millie? Millie is simple. Millie, then it is meter or something, anything, millimeter. Let me consider here meter. It can be Dalton or milliliter or any measurement, right? So millimeter, again the relation is minus 3 meter. Then after milli, it comes micro. So Millie took a micro nap. The bold letters are like the things that bold and underline will represent the mnemonic. So micrometer, micro is micrometer, again the jump is 10 to the power minus 6. So you will remember the sequence. If you remember the sequence, you can easily like understand what is the relationship with meter, right? So after micro, what comes is, there are 3 letters, as we can see, 3 letters, N, A and P. There are 3 letters. So N represents the, very easy, N represents nanometer. So the jump is 10 to the power minus 6 to minus 9. And trust me, if you like practice this 2 to 3 times, you will by like instantly know what is the nanometer, what is the relationship between nanometer and meter. It's just about practice. But for initial steps, this mnemonic is really helpful. It helped me a lot in like stress situations when I don't remember what is the relationship with picometer and meter. So N is nanometer and P is picometer, right? Picometer, and the jump is again 10 to the minus 12. So the question is, what is A? What is this A? And even this, you can see that I have left a gap here, right? Why? Because this is where the angstrom comes in. Angstrom is a very, very, very important unit in biology. This is the angstrom. Angstrom. Okay. So 1 angstrom is equal to, since it comes after nanometer and nanometer is already 10 to the power minus 9 meter, just it will add one more 10 to the power minus 1, that is it is 10 to the power minus 10 meter. So this is where you, the mnemonics comes to life, that A stands for 1 angstrom, that is 10 to the power minus 10 meter. The angstrom, like it in, you know, what is that term that happens in DNA? I don't remember, like ethidium bromide, what is that, stacking, anyway. The angstrom like goes into between the nanometer and the picometer. So 1 angstrom is 10 to the power minus 10 meter. Okay. Okay, so these are the like smaller units that we have covered so far. Now let's see the bigger units, that is beyond kilometer or beyond hectometer. Beyond kilometer, there are only three things that you need to remember, that is mega, then again meter. What is megameter? Since kilometer is already 10 to the power 3 meter, so megameter is equal to 10 to the power 3 plus 3, that is 10 to the power 10 to the power 6. 10 to the power 6 meter. After mega comes the giga, that is giga is 10 to the power, again the jump is for 10 to the power 3, that is 10 to the power 9. That is why I told 10 to the power like 3 is the magical number. Mega, giga, and then there is tetrameter, that is 10 to the power, again from 9 the jump is 3, that is 10 to the power 12 meter. Okay, so what are the symbols used here? As I told you, when we are decreasing the, like when we are going beyond millimeter, the symbols are always small letter, smaller case. So for the bigger units, the symbols are in uppercase. M for capital M for mega, capital G for like giga, and capital T for tetra. The reason why I didn't make any mnemonic for this one, because we are like all familiar with MB, megabyte, gigabyte, terabyte, and by like instance we know that gigabyte is greater than MB, or the terabyte is greater than like gigabyte or MB. Okay, so this is why the mnemonic is not required. You can just remember like in the form of memory bandwidth, that is MB per second or GB per second or terabyte per second. This is the internet speed that we all commonly use. This is like found in very rare cases, and I don't know where this is found, maybe in Google headquarters. Okay, so this is how you can remember. I will just remove it so that it doesn't get confusing. Okay, so these are the some of the SI units that are commonly used in biological and system and bioscience, and you also find these SI units in various numericals. Okay, now apart from this, there are few like measurements that as biologists everyone should know. What is the molecular weight of water? And normally in biological system we measure molecular weights by Dalton. Not only biological systems, in like chemistry also. Water, glucose, hemoglobin, and insulin. Now there are insulin. Now there are many more that we should know, but I think these are the top 4 that every licensed student should know. So what is the molecular weight of water in Dalton? That is 18 Dalton, and it is very simple to like calculate. Water formula is H2O. The molecular weight of H is 1, so 1 into 2 for this 2. There are 2 hydrogens, so 1 into 2 plus oxygen's molecular mass is 16, so 1 into 2 is 2 plus 16, that is 18 Dalton. Okay, and you can also calculate for the glucose. You can just draw the structure of glucose. CHO, CH2OH, and this 1 2 3 and 1 2 3 4 5, and I think there will be another one. Yeah, and for this one H will be here, and HOH, H and OH, okay, and these are the carbons. Okay, so if you calculate the molecular mass, it will be 180, but the very simple way to remember this is 10 times the water. 10 times the molecular mass of water is glucose. Okay, so for hemoglobin, the molecular mass is 64 kilodalton. Now this is why we need to also remember the bigger units. So kilodalton means 64,000 dalton. This means, let me write it here, this means 64,000 dalton. Okay, 1 kilo dalton is 1000 dalton, so 64 kilodalton is 64,000 dalton. Okay, so what is the molecular weight of insulin? Insulin is 5.8 kilo dalton. It is less than hemoglobin, and it's of course makes sense. Hemoglobin is a tertiary structure and a big structure, and like made up of 4 subunits, and insulin is not that, obviously. So insulin is 5.8 kilodalton. Again, 5.8 kilodalton means 5.8 into 1000, that is 5800 dalton, right? 5800 dalton. Okay, so these are the like common SI units and common measurements that we need to know, and this is the mnemonic that will help you to remember these SI units. And okay, so what is dalton? Dalton is 1 dalton is equal to 1.6 into 10 to the power minus 24 gram. It is written here in the upper section. I think you can see this written here. So here we are discussing about the daltons, right? Here is the dalton, 180 dalton, 64 kilodalton, 64,000 dalton. So what is the relationship with dalton and gram? It is 1.6 into 10 to the power minus 24 gram. So 1 molecule of glucose is 180 into 1.6 into 10 to the power 24 minus 24 gram. That is the molecular weight of 1 molecule of glucose in gram. Okay, this makes sense, I think. So let's go to the next page. Yeah, so here are two websites that I have given, very interesting website. The first one is the bio numbers. So if you click on the website, and the links in the PDF are clickable, so you can just hover your mouse on the link and just click it and it will open. Otherwise, you can copy the link from the PDF if it's not opening by clicking. Ideally, it should open. Okay, so bio number, this first website will look something like this one. And if you go in this website, you will find like many interesting biological numbers. Like you can already see here the number of hairs on human head, or average duration of single eye blink. And not only that, you can also see some examples, that is ribosome coiling, or ribosome coli, or E. coli, or transcription, or P53 human, or like mitochondria, and what is the density, what is the volume, what is the radius, length, anything of any cell organelle or any virus or anything, E. coli, or like Saccharomyces cerevisiae, what is the measurement of that. So you can find all the almost all the biological items and their measurements, the weight and the density and everything in this website. It's a very interesting website. You can play around here. But then if you go into the book section, you will be directed to this website. Okay, I have also given a separate link for this one. This website, the second link, this is the first link. Okay, sorry, this is the first link, this is the second link. If you go to the second link, this one is the second link. If you go to the second link, you will find this kind of page where this kind of page where various interesting facts are given, what is the, how big are viruses, or how big is a human cell, how big is a photoreceptor. These are you don't have to search it. There are some predetermined measurements that are given. That is very interesting. I will go on also read about it and learn the measurements also. And you can I will tell you to go and download this PDF also, that they have released on SARS-CoV-2 by the numbers. It is a really interesting one. Okay, if you have interest in knowing various measurements in biology, then you can just roam around this. Okay, so the next page, and in the next page you will see some biological measurements, common biological measurements. That is very important, and I have left some gaps in here to just write it right now. What is the average radius of protein? Okay, so the average radius of protein is in nanometers. I think anyone should remember these units, right? Because a nanometer and an angstrom is very different, and the units are really important if you're defining something. So these units are really important, and let me just fill in the gaps here. So average radius of protein is 2 nanometer. Now again, the word average is important because this is not the radius of every protein, obviously, but the average radius of protein is 2 nanometer, and average volume of protein is 25 nanometer cube, obviously, because it is a volume, it has to be in cubes. Okay. Average mass of amino acid. Now, there are two cases, that is the non-bonded and bonded form. Again, the average term is very important. The mass of amino acid is not equal for all of them, but it is an average one. So this mass is very important when we are calculating like the mass of the polypeptide or anything. So this mass of amino acid is very important. So in the non-bonded form, that is a nascent amino acid, the mass is calculated as 128 Dalton. That is the average mass of one amino acid, right? But when they are in the bonded form, like this is an amino acid and this is an amino acid and this is an amino acid, what is this form? This bond is peptide bond, and we know that whenever there is a peptide bond happening, we lose one molecule of water. This is why knowing the size of the water is really important. The molecular weight of the water is very important. What is the molecular weight of water? Just now we saw that is 18 Dalton. So when two amino acids are linking, we have to subtract one water. So simply, if we do 128 minus 18, it comes 110. That is 110 Dalton. This is the average molecular weight or more molecular mass of amino acid in the bonded form. Why? Because it is losing 18 Dalton, that is 1 molecule of water. And for non-bonded, you can consider it as 128 Dalton. Okay, so what is the protein concentration in cytoplasm? It is like around 150 mg per ml. Again, the unit is very important. And what is the thickness of lipid bilayer? And I will just come to like the discussion why these measurements are really important. You can think that we can Google it every time, but trust me, when you are solving numericals, Googling everything is not the solution. You need to remember some of this in your mind. So what is the thickness of lipid bilayer? The thickness of lipid bilayer is 5 nanometer. 5 nanometer, that is the thickness of lipid bilayer. Okay. And then the next is, what is the mass of lipid molecule? That is 800 Dalton. Again, I am telling that here the average term is not written, but just assume average in front of every point. Average mass of lipid molecule is 800 Dalton. Then again, the average diameter of nucleus is 5 micrometer. This is micrometer. Again, the unit is important. Micrometer. What is the length of mitochondria? That is 2 micrometer. As you can see, the most of the cell organelles are in the range of micrometer, right? Micrometer. Now, genome length of human genome. Why I included this? Because it came from a revolutionary project, that is Human Genome Project. How many years did it take? Almost 13 years, right? Okay. And what was the cost? Any guess? Just look it up in the internet and then compare the cost of sequencing one human genome today and the cost of sequencing one human genome in this Human Genome Project. You will understand how far we have came in terms of biotechnologies. Okay. So genome length of human genome, that is 3.2, not million, it's a billion. 3.2 billion base pair. It is in billions, not millions. Almost approximately 3.2 billion base pair. That is the genome length of human genome. Okay. Now, mitochondrial genome of human, it has approximately 17,000 base pairs and total of 37 genes. And what does 37 genes code for? It codes for 2 rRNA, 22 tRNA, and 13 polypeptides. Okay, this is some generic information about mitochondrial genome of human. How many genes? 37 genes. What is the number of base pairs? 16,900 something. So approximately I wrote 70,000 base pairs. Okay, and this is also important. Sometimes in many competitive exams, this will be asked, how many polypeptides or how many tRNAs or how many rRNAs does mitochondrial genome of human code? 37 genes, 2 rRNAs, 22 tRNAs, and 13 polypeptide. Okay, great. So Diameter of DNA is very simple, it is 2 nanometer. Okay, almost everyone knows this. Now I will come to the discussion why remembering these things are important. What is the diameter of water? Like, what is the unit of diameter of water? Just forget this numerical, but what is the unit of diameter of water, and why this unit is very important? It is angstrom. So this is like 10 to the power minus 10 meter. Okay, and how much angstrom? Approximately 2.7 angstrom. Now we all know that water is polar and our cell membrane is non-polar. Non-polar. Why I am like focusing on this non-polar word? Because they don't go hand in hand. You cannot mix polar with non-polar, and we know that polar molecules do not pass through like cell membrane. That is why cell membrane is selectively semi-permeable. But the question is, how does water pass through the cell membrane then? We all know that there are ion channels, or like there are aquaporins, right? There are aquaporins, and this is aqua means water, and this is where the and porins means the channel, and this is where water channels. This is how water passes through the membrane. But let me tell you that most of the cases, in case of simple diffusion, water does not need aquaporins to pass through the cell membrane. During simple diffusion, if these are the cell membranes, lipid bilayer, and you can imagine same. In the lipid bilayer, water molecules can actually pass through the lipid bilayer without any channel. Why? Because the size of the water molecule is so small, it is 2.7 angstrom, that this size allows the water molecule to pass and like to squeeze between the lipid membranes and pass the lipid membrane without any channel. This is why structural biochemistry, or knowing the basic structure and molecular weight of and the dimensions of biomolecules, are very important, because this is the concept that is, let me write it down, small. The word is small, it is important. Small, trust me, this is S. So small molecules, even polar one can pass through lipid bilayer even though it is non-polar. So this is the concept, that small polar molecules, and obviously non-polar molecules can diffuse through the lipid bilayer, but small polar molecules can also like pass through the lipid bilayer membrane because by simple diffusion. So why do we need aquaporins? Because simple diffusion is a very slow process, and whenever we cannot completely rely on the simple diffusion process. So we have aquaporins. There's the water gates. So through water gates, the like transport of the water is really much faster than diffusion. But in under normal cases, simple diffusion due to the size of the water, it can pass through the lipid bimembrane. I think we are done with this slide, and now next slide. Okay, so here is a question, and the question says that the equilibrium constant is given this. What is the equilibrium constant of this reaction? This reaction, ATP to ADP, and we are all familiar with this reaction, right? The breakdown of ATP to ADP and inorganic phosphate. So the equilibrium constant for this is given. Let me write down the values. K equilibrium is 2 into 10 to the power 5. This is a bad handwriting. Okay, 10 to the power 5. What is this? Molar. We'll come to it also. Like 1 molar, what is normality, what is molarity, what is like molar versus mole and normal. I will come to this, but for now bear with me. So K equilibrium is given 2 into 10 to the power 5 molar, and what is the reaction? That is ATP. It is breaking down into ADP and inorganic phosphate. This is nothing but inorganic phosphate, not a fancy, like it may look like a fancy chemical compound, but this is nothing but inorganic phosphate. Okay, so in this case, this part is the substrate and this total part is the product, right? So for finding like any reaction quotient Q, what is the formula? We divide the concentration of product by concentration of substrate. By the way, if I am writing anything in this bracket, then this represents in like chemistry, this is a normal thing, that if you are writing anything in this bracket, it represents concentration of A. If I am writing B, this represents the concentration of B. Okay, so this is representing the concentration of P, and this is representing the concentration of S substrate. So we have two products. So in this case, the formula will be concentration of the multiplication of these two products, that is the multiplication of concentration of ADP and inorganic phosphate concentration divided by the concentration of substrate. Okay, so what is the question? Sorry for the sound. What is the question? In a given cell, the concentration of ATP is 5 millimolar. Let me write that down, the like important things. That is, the concentration of ATP is 5 millimolar and the concentration of ADP is 0.5. Concentration of ATP is 0.5 millimolar and the concentration of inorganic phosphate is millimolar. Okay, this is ADP. I think this is clear now. Okay, so the question is this reaction in the given cell at equilibrium? So we have to check that in under these concentrations, is this reaction at equilibrium? The equilibrium constant is already given, so we have to find this Q and compare with the this one, equilibrium constant. Okay, so if the Q is less than or greater than equilibrium constant, then the answer is no, the cell in the given condition is not at equilibrium. So let me just plug in the values here only, and we will find the Q value. So what is the concentration of ADP in this? Concentration of ADP is 0.5. Okay, so normally I recommend to write the units also, so that like in many cases cancelling out the unit or the unit gives us a huge problem. So if there are, especially in different units, right, like one of them is in micrometer or one of them is nanometer and one of them is millimeter. So if you write the units in the equation, if the equation is not big enough, then you will not like confuse yourself with so many units. So the concentration of ATP is 0.5 millimolar. The concentration of inorganic phosphate is into 5 again millimolar divided by the concentration of ATP. What is the concentration of ATP? 5 millimolar. Okay, 5 millimolar. Sorry about that. Yeah, so concentration of ATP is 5 millimolar. If we cancel out this 5 millimolar, the concentration is 0.5 millimolar. Now again, the unit is in millimolar, but we need to find, like, compare in moles. This is where unit conversion comes into play. 1 millimolar equal to 10 to the power minus 3 molar. Okay, so 0.5 millimolar equal to 0.5 into 10 to the power minus 3 molar is equal to 5 into 10 to the power minus 4 molar. As you can see, this is in minus 4, and this one, okay, let me rub this one. Yeah, so this is in 10 to the power 5. So you can clearly say that Q is very less than K equilibrium. So the answer to this question is no, the cell at the given condition is not at equilibrium. The next question is in which direction the reaction will proceed. Okay, so let me give you a quick concept. This is K equilibrium, this is Q, and this is also Q. Okay, so if this is K equilibrium and this is Q and this is Q, so if the Q is less than the K equilibrium, the reaction will proceed in the forward direction, and if the Q is greater than K equilibrium, the reaction will move to reverse direction. For in this case, our Q is much less than K equilibrium, so the reaction will proceed towards the forward direction, that is more ATP will be produced in this cell under these conditions. Okay. Let's move to the next slide, and I think we're done with the SI units and the commonly biological measurements. So let's dive into the next topic, that is log properties and calculation of logarithmic values without using the calculator. Okay, so in this slide we can see many like log values and log properties. Don't get overwhelmed with anything, I will explain them one by one now. Okay, so there are two things that you can see, that is ln and log. Okay, the ln and log. So ln is nothing but log with base e, and what is e I will come in the next slide. Log with base e is ln, and here is the relationship between ln and log. And even when only log is written, it is with base 10. Okay, it is with base 10. So ln is log with a base of e, that is Euler's number. E is Euler's number, and log is with base 10 if nothing is written. So these are the few values that you need to remember, and there is a white dotted line here, as you can see this one, and there is a reason I have put it there. I will explain you later. So you have to remember that ln1 is equal to 0 and log1 is equal to 0. Okay, ln1 or log1 is equal to 0. ln2, let me zoom it. Yeah, ln2 is almost equal to 0.7, and ln3 is almost equal to 1.1. You can actually don't care about ln3 and ln5. You don't need to remember these two. Even if you remember ln1 and ln2, it is sufficient enough for like 90% of the numericals. Okay, so ln1 is 0, ln2 is 0.7 almost, and lne is equal to 1. Why? Because ln stands for log e, and log e to the power, again log e of e is 1. Okay, so ln1 is 1. So from this you can guess that what will be the value of log 10. If here is 10 and here the value is 10, the log 10 is equal to 1, as you can see here. Same thing, log base 10 of 10 is equal to 1, and I will tell you why this is happening. The log 10 of 10 is 1. I will tell you that. Okay, so in the ln chart, ln1 is equal to 0, ln2 is equal to approximately 0.7, and ln10 is 2.3026. This number is extremely important, because this is the number that we use to convert ln to log. This is extremely important. Okay, don't forget this under any condition. Okay, so ln10 is 2.3026. We can write this 26 as 3 because it is very far from point, so this becomes 2.303. okay, remember this one, 2.303. ln10 is 2.303, and this is the number we use to convert ln to log. ln x is equal to 2.303 log x. Okay, so x can be anything. So if you need to convert anything from ln to log, we use 2.303. okay, so value of log 1 is 0, value of log 2 is 0.3. You don't need to remember this part. 0.3, log 3 is 0. Almost 5, not 5, almost 5, and log 5 is almost 0.2. and yes, obviously you can see the link that ln2 is 0.2, log 5 is 0.7. You don't need to connect both of them, but it is what it is. Log 5 is 0.7, and log 3 is 0.5, and log 2 is 0.3, and log 10 is 1, as I told you, and log e is again e, not 1, e, because the base of log is not e. If it was e, then it would have been 1, but it is not e, so it is not 1. Log e is e. Okay, so from here only you can, okay, let's see the properties, then we will come to the next part, this one. Okay, you don't need to remember these parts. You can derive these parts on your own. That is the beauty of knowing the properties of the logs. Okay, so the first property is the product property. Okay, so the product property, so log with any base when two numbers are multiplied, you can add those two. I think many of you already know this, I'm just revising this one. Okay, so log of 2 3 is equal to nothing. This is log 23. Okay, not 2 3. Log of 2 into 3 is equal to log of 2 plus log of 3. And we know that if the base is 10, I'm considering the base is 10, we don't need to write 10 every time because by default it is 10 if nothing is written. So log base 10 of 2, log 2, what is the value of log 2? Equal to 0.3 plus log 3 is 0.5. Again, these are approximations, so if you just put into the calculator, it will be very close to what I'm writing here. So the answer is like almost 0.8. So if we like want to remove the approximation to a little bit, it can be like close to 0.78. Okay, we can write that 0.78. How 0.78 is coming? It is not coming from anywhere. We are just approximating like 0.8 to 0.78, approximately 0.78. You can just check on the calculator afterwards, like what is the value of log 6. Okay, I think it is written here. No, up to 5 is written. Okay, anyway, so log 6 is equal to 0.78. And see this, to find the log 6 you don't need to find the calculator every time in your bag. So log 6 is equal to log 2 into 3, and we know the value of 2, we know the value of 3, and we can find it like this. Same way we can find the value of log 9 also. 3 into 3, that is log 3 plus log 3, that is log 9 value is close to 1 but not 1. Obviously log 10 is 1, so log 9 is log 3 and log 3, that is 2 into log 3, and 2 into log 3 is 2 into log 3 is 0.5 but not completely 0.5, as we know that we are approximating it. So approximately will be 1 but it will be not 1, it will be something like 0.97 or 98 maybe. Just check on the like calculator, you will find it. Okay, so approximately you know the value of log 9 log 6 without like touching the calculator. Okay, so the next property is quotient property, that is division property. So this one is nothing but the like manipulation of the first one, that is log m divided by n is log m minus log n. Okay, so in case of multiplication it is plus, in case of division it is like minus. So if we take an example, log 3, let's consider that we don't know the value of log 3. Okay, so log 3 will be equal to, we can write 3 like this, 6 divided by 2, right? So if I can write log 3 as 6 divided by 2, we can write log 6 minus log 2, right? And from this value, we have seen that the log 6 value is almost 0.78, right? And the log 2 is, we know that log 2 is 0.3. So this is 0.3, log 6 is 0.8, log 2 is 0.3. What is the final value? The final value is approximately 0.48, and you can see that log 4 is approximately 0.48, right? 0.477771. So this is approximately 0.48 or very approximately 0.5. So this is correct, this method is working, right? So you can find like log anything, log, I don't know, 4 5, you can just find it like this. 5, what will be the value of log 5? Log 5 you can write by 10 divided by 2, and log 10 is 1, log 2 is almost 0.3, 1 minus 0.3, that is 0.7, right? Log 5 is almost 0.7, as we can see here also, the log 5 is almost 0.7, right? Okay, so the next property of log is power property, that is whatever in the is in the power, it comes in the prefix, it comes before the log. So if we take an example of log 100, we can write log 100 as log 10 square, and just now we saw that this power will come in front, that is 2 into log 10. And what is the value of log 10? The value of log 10 is 1, so this becomes 2 into 1, that is 2. Now let's get back to the like down this dotted line, down this big numbers. So what is the value of log 100? The value of log 100 is log square, that is 2. That is what we found just now. So the thing is that you just need to remember 1 2 and 3 4, and here 1 2 3, and this you can also forget, like log 5 you don't need it much, you can just derive it from 10 by 2. So by this 4 to 5, remembering this 4 to 5 values, you can find like all these values and are many more, right? So this is the beauty of knowing the logarithmic properties. You don't need to like search for the calculators every time. So log 100 is 2 log 10. Similarly, log 1000 is 1000 means 10 to the power 3. 3 will come into the front, 3 into 1, that is 3. And what is log 1 by 10? 1 by 10 means 10 to the power minus 1, and minus 1 will come in front. Then minus 1 into log 1, log minus 1 into log 10, and log 10 is minus 1 into 1, that is minus 1. Right? Similarly for the 100, that is 10 to the power minus 2, and the value of 1 by 100 is 10 to the power minus, the value of 1 by 100 is minus 2. Minus 2 into 1, that is minus 2. So you can like get all these values just by remembering the log properties. Okay, now there are few more properties that we need to see, that is log b, like the base is b and the number is a. So this is called the change of base property. Okay, so log b base a is, you can change the like add a new base to the log. I will just explain it with an example. Okay, it will be better, I think. Let me change the color of the pen. Log 3 with base 2. Now the log base is not 10, it is not e, it is really complicated looking if you don't know the properties. But log 3 of base 2, we can convert this in log of something we know, that is log of base 10, and a is here means it is 3 divided by log of base 10, that is 2. Now we can solve this, right? So log 3 of base 10 is, what is the value? That is almost 0.48, divided by log 2 of base 10 is 0.3. So the answer comes approximately 1.6, right? 3, yeah, 1.6. So log 3 with base 2 is equal to 1.6, and you can also check in the calculator. And the most astonishing part is that this, before knowing this property, this like this logarithmic property looks impossible to solve on like by mind only, right? But if you know the property, you don't even need to touch the calculator. You can just write it in a different form, and you know the value of log 3, you know the value of log 2, and you can just determine the value of log 3 with base 2. That is 1.6, approximately 1.6. It may be 1.58 or something like that. Okay, so you get the idea. Okay, so when there are two log values, that is log a with base b and log c with base b, that is same value, same log with same base, then a equal to b. Let me tell with an example, that is log 3, the base is 10. I don't need to remind you again and again. Log, let's say 3 into 1, so that it makes sense, right? So in this case, you can like say that the logs are cancelling out, but again it is not mathematically correct. But anyway, for us we will say that the logs are cancelling out, and 3 equal to 3 into 1, and which is a like correct one, we know that. Okay, so you can check with any value if two numbers are given and the base of the logs are same, then a equal to c. Okay, the another property is log a with base b. This property is very important. Like we use this a lot of times in population growth kinetics. You will also see that population growth kinetics is in tomorrow only, day 2, right? So we will see this property in there also. Okay, so log a with base b equal to c. So a is equal to b to the power c. This is why log is important. Like if a equal to b to the power c, how can we convert this equation into a logarithmic form? So log a with base b, log a with base b is equal to this exponential, that is c. Okay, let's understand with an example, that is 16 is equal to, let me change the color, yeah, 16 is equal to 2 to the power 4, right? So we can convert this into log, that is log 2 of 16, log 16 of base 2 is equal to 4. You can also check it in the calculator, it will come the same. So these are the few properties of logarithmic functions, and by using these properties you can like derive any, or not any, like almost all the numerical problems that you normally face in your day-to-day exercises or competitive exams. You can solve it within seconds without like ever needing to touch the calculator. And in many exams I think calculator is also banned, right? So you need to know these logarithmic properties, is very important. So do I need to like do a quick recap? I think it will be good, right? So what did we learn? Log 2 is 0.3, log 3 is almost 0.48, or you can also say 0.5, log 10, and again if you practice it like 1 or 2 times it will just be a muscle memory. And for ln2 is 0.693, that is equal to 0.7, not equal to, like similar to 0.7. And then ln5 is equal to 0.7 also, not ln5, sorry, log5. Log5 is like equal to 0.5. And these are this, and there are some properties like log m into n is equal to log m plus log n. Okay, so these are some of the properties, and these are some exercises that we will solve right now. So if x equal to log y, then y equal to 10 to the power x. Yeah, this is a, like you can say, a new property, but if you play around with the first one you can understand that this is the base. So this is like equal to this property, this one, the last property that we studied, right? This one, yeah, right. So if y equal to, if x equal to log of y, that with base 10, then y equal to 10 to the power x. And this is very important, like for solving many numericals you will like very often face with these problems, that is something is equal to log something with a known base, so you have to find y. So y becomes, that is the anti-log, like anti-log, this is called the anti-log. If this is equal to this, then what is the anti-log? So anti-log is nothing but the base of the log, and this left hand side becomes the exponent. That's it, that is the whole concept of anti-log. Okay, just you have to like multiply this. If x equal to log base 10 y equal to 10 to the power x. Why 10 to the power x? 10 is coming from the base of this log 10. Okay, so similarly you can apply this logic to here also. Ln, what is the meaning of ln? Ln means nothing but log base e x equal to y. So what will be, this x will come here, e to the power, this will come here, e to the power y, right? Simple. Okay, I think this is correct, right? Yes, it is correct. Okay, so whatever the base is, base will come in the front, and like the equal, that is the right hand side of the equal to form, we will come to the exponent part. Okay, so log 10x again equal to y, will be y be equal to this 10 comes here, 10 to the power x. Sorry, the x is equal to antilog. What is the value of antilog? 10 to the power y, right? So here also the antilog of y is e to the power y. Why? Because the base is e. Very simple. Okay, so again this is the exercise, that is log base 10 of x equal to y. So it is the value of x. Again there is the antilog. Antilog is nothing but 10 to the power y, because y, 10 is the base value. Okay, so what is e? What is e, right? E is nothing but Euler's number. Euler is the name of the scientist, Euler's mathematician, Euler's number. And what is the value of Euler's number? The value is, I think you should remember this one, 2.71828, or you can just simply write 2.72. Okay, so the value of Euler's number is 2.71828, or it is very like approximately it is 2.72. This is E. Okay. Okay. So from these properties, now we can say that if log b with base a is equal to c, then b is equal to antilog, that is the base will come here, a to the power c. This was the main concept. If log a the log b of base a is equal to c, then anti-log, this anti-log is nothing but the base will come to the front and a to the power c, that is b equal to a to the power c. Okay, this is the this is the concept of anti-log. So now you can solve anti-logs on your own also. So what is the anti-log of, like, I don't know, 2, that is 10 to the power 2, then it is 100. Okay, so let's do this exercise. Find the value of 27. Again, if you don't know the, like, properties, it will be really hard, but now we know that log 27 is equal to, sorry, log, what is it, 3 cube, right? We can write 27 as 3 cube. So the exponent will come in the front, that is 3 log 3, that is 3 into, what is the value of log 3? 0.48, right? 0.48 is, okay, you can consider 0.48 as 0.5. So 0.5 into 3 is 1.5, and it will be slightly less than 1.5. So let me write 1.4. Okay, so log 27 is approximately 1.4. Log 5, again, log 5 is, like, if you don't remember log 5, no issues. Log 5 can be written as 10 by 2, right? 10 divided by 2 is 5. Then again, using the log properties, log 10 minus log 2, I think by now you have got the hang of it. Log 10 is 1 minus log 2 is 0.3, and it is approximately 0.7, or you can also say like 0.69, right? And let me check this value. Log 5 is, from our calculation, it is 0.69 or 0.7. Okay, let's check whether it is true. And here we can see that I have omitted this one, but log 5 is actually 0.69, or it is very close to 0.7, right? Just to 0.7. Okay, okay, so I think we are done with the logarithmic properties, and now let's dive into the concepts of mole, molarity, and normality. Okay, so there are 3 terms, that is, 1 is mole, and 2 is molarity, and 3 is normality. Let's see the definitions, the basic definitions. Okay, so the basic definition of a mole is, and the mole and molarity and normality is written here. So I will not bore you with the definitions, you can read it from the slides. So the concept of mole I will discuss in the like next slide, but we need to see that the formula of molarity is number of moles of solute divided by the volume of solution in liters. Okay, just let me go to the next slide only. Okay, so firstly, that is mole, right? Mole, mole, M-O-L-E. What is the concept of mole? The concept of mole is very simple. Just divide the given mass, given, like, weight divided by the molecular mass of that substance. Anything, like, it can be, I know, atoms, molecules, and any entities that is present, that is the given weight of that entity, that is given weight of atom, or given weight of molecule, or given weight of, like, ion, divided by the molecular weight of that entity. Okay, so, like, you can say that in a given solution, 3.6 kg of glucose is there, and what is the, find the number of moles, right? So this is the given molecular weight. So let me solve this one. 3.6 kg, it is the given like weight, like molecular weight. 3.6 kg is 3600 gram, right? So therefore the mole is, what is the mole? The given molecular weight divided by the molecular weight of that molecule. And this is why we need to, like, remember the molecular weight. In the first or second slide, I think I showed you that the molecular weight of glucose is 10 times water, and what is water? 18, that is 180, right? If we cancel this out, it comes 20 moles. So this is how you find the moles. It is nothing but the division of given molecular weight divided by the original molecular weight of this, that, like, atom or ion or molecules. Okay, now we cannot write 20 moles like this. This and this are not equal. This is not correct. 20 moles means 20 moles. You have to write this moles, or you can also write 20 mol, mole, but not m. Mole and m is different. Okay, so what is m? Now let's come to this part, that is molarity. Okay, so before coming to molarity, one second, I will discuss ways of finding moles. Not only this is the way of finding mole when the mass is given. In many numericals you will find that the number of molecules is given. Okay, so how will find that the what is the like how many moles are there. So the formula is nothing but number of like entity. I am again using entity because not only atoms, the mole concept applies for molecules and ions and everything. Okay, so number of the given entity divided by the Avogadro number. What is the Avogadro number? It is 6.023 into 10 to the power 23. We have been studying this like since our childhood chemistry. The Avogadro number is 6.023 into 10 to the power 23. So for finding mole, you will divide the number of molecules that is given divided by Avogadro number. And what happens when the data is given like in the volumes, right? In the volumes, just convert the volume, the given volume in liter. Remember the unit in liter, always in liter, divided by 22.4. Okay, why do we have to convert the volume in liter? Because this 22.4 is in liter. So the number of mole is, what is the number of moles of, suppose like 20, what is the number of moles of 22400 liter of, I don't know, nitrogen or carbon dioxide or anything? Nothing, just divided 22400 liter by 22.4 liter and just cancel these things out. Okay, so this is how you find the mole, and this is whatever be the result, this is the number of moles. Okay, done. So this was the concept of mole. Now why these two are not equal, why you cannot write like this? Because this is a symbol of molarity. What is molarity? Molarity. What is molarity? If we go back to the definition, what does definition says? Definition says that molarity, often denoted as M, is a measurement of the concentration of the solute in a solution. It is the measurement of concentration of a solute in a solution. It is defined by the number of moles of the solute, okay, dissolved in 1 liter of the solution. That is number of moles per liter of the solution. Mathematically, M, that is in capital M, is calculated by this formula. What is the formula? Molarity M is given by moles, that is the number of moles. It is not only moles, you have to write the number of moles, that is number of moles of solute divided by the volume of solution in liters. This is very important, not in ml, not in anything else, this is in liters. Okay, so I will discuss it in the next slide. So what is the formula? What does the formula becomes? The formula becomes number of moles per liter of solution. Okay, number of moles per liter of the solution. This is the formula of molarity. This is the concept of molarity. Okay, so from this example only, what is the relationship between this 20 moles and molarity? So let's start from here. If like the glucose is 20 moles in 2 liter, if this 20 mole is like present in 2 liter of the solution, find the concentration of glucose in molarity, right? In molarity. So how will you solve that? Very simple. Now that you know that the number of moles, again the formula is number of moles per liter of the solution. So 20 mole is present in 2 liters, right? So what is the like number of moles present in 1 liter? 20 divided by 2, that is 10 m. So that is why 20 molar is not equal to 2 capital M, because capital M represents molarity, and if the total volume of the solution is not given, you cannot find the molarity. So like 20 mole in 2 liter is equal to 10 molar. Okay, this is the concept of molarity. Now like dive into the concept of normality. This is very important. In many cases you will find that like in many questions it is given that two normal hydrogen chloride or like H2SO4, right? That is not a normality, that is like that is not molarity, that is normality. Li ty. Okay, let's go to the definition because like yeah, definitions are important. It is defined as the mass of substance that is equivalent, here is the mass of substance that is equivalent to the reaction of 1 mole of proton or electron in a given chemical reaction. What does that mean? It is the mass of the substance that is equivalent to the, this is where the equivalent terms comes. Okay, equivalent to the reaction of 1 mole of proton or 1 mole of electron. That is for acid the gram equivalent, this is a new term, the gram equivalent is the mass of acid that donates 1 mole of protons. So what does the concept say? The concept says that if like the mass of the acid is 98 and it is donating 2 moles of like hydrogen ions, then the gram equivalent weight of that acid is 98 divided by 2. Why divided by 2? Because we need to find the mass that is donating 1 moles of, that is equivalent to the donation of 1 mole of proton. So 98 is donating 2 moles of hydrogen. So what will be the like equivalent gram that is donating 1 mole of hydrogen? It is equal to 98 by 2, that is 49, right? So this 49 will become the gram equivalent weight of that acid, whatever the acid is. It is a divalent acid, right? So it is like giving 2 hydrogens out, so it is a divalent acid. So for every divalent acid we have to divide the molecular weight by the number of moles the protein is given. For divalent it is 2, so we have to divide it by 2, right? So this is nothing but the molecular weight of that acid. So this molecular weight is giving 2. So what is the gram equivalent? Gram equivalent is weight that is giving only 1, so we have to divide the molecular weight divided by number of hydrogen ions that is given, so it is 2 and the answer is 49. Same for the base, what is told here. And for a base, the gram equivalent weight, now we are familiar with this term, right? The gram equivalent weight is the mass of base that accepts 1 mole of proton. So the concept is again same. If like our base accepts 2 mole of hydrogen, then the gram equivalent will be the molecular weight divided by the number of moles of hydrogen it is like accepting, and that will be the gram equivalent weight, right? So again, if I take the same like example, suppose a base has 98 molecular weight and it is accepting 2 hydrogens, so the gram equivalent weight will be 98 by 2, that is 49, right? Okay, so now I think the concept of gram equivalent weight is clear. Gram equivalent weight is not equal to normality. We are just clearing the concept of gram equivalent weight. Okay, so the formula of gram equivalent weight is molar mass divided by n. What is the n? Again, it is the number of moles that the acid is number of moles of protons or electrons that is the acid is giving or accepting. Okay, so what is the formula of n then? The formula of n is the number of equivalent of solvent, that is the number of gram equivalent divided by the volume of solution in liter. This is the formula of normality, that is number of gram equivalent, not gram equivalent, number of gram equivalent. Now let me show you what is the meaning of number of gram equivalent. It's a big term, right? So let me break it down. Number of gram equivalent. Okay, so suppose like for HCl is monovalent, right? HCl is monovalent. It will be dissociated like this. Sorry, this is not chlorine, this is chlorine. So it is giving out one hydrogen hydrogen ion. So what is the molecular mass of this? Molecular mass of this is say 1 plus 30 like 7, right? What is the molecular mass of chlorine? 37, I think it is 37. Let me check. Uh, molecular mass of CHLORNE. I think it is 37. Oh, sorry, this is 35. 37 is like isotope or something maybe. Okay, so the mass of chlorine is 35. So the total value is 36, and since it is only one mole, that is gram equivalent weight will be 36 divided by 1, that is 36. So for monovalent atoms, the molarity becomes the normality. Why? I will just show you. So this is the gram equivalent weight of HCl, and in case of H2SO4, what happens is it gives two hydrogen atoms and one SO4 minus 2, right? So this is giving two hydrogen atoms, and this is the example I took in the previous slide, that is the mass of H2SO4 is 98, and this is giving two hydrogen atoms. So the gram equivalent weight will be 49. Why? 98 divided by 2 is 49. Okay. So now, what is the number of gram equivalent? Number of gram equivalent means, suppose like it is given that 196 gram of H2SO4 is given. Okay, so 196 gram of H2SO4 is given. So in 196 gram, how many gram equivalents are present? So simply we have to divide, right? So number of gram equivalent weight is equal to the given molecular weight divided by gram equivalent weight. Okay, so this is the n. This is the number of gram equivalent present in 196 gram, right? Makes sense? Okay, so number of gram equivalent equal to given weight divided by gram equivalent. Okay, and so what is the formula of normality? Normality is this divided by, I will just grab all of it. Yeah, okay, so normality is equal to this number of gram equivalent by volume in liters. Okay, just let's solve one problem. I think that will make it more clear. So in this problem, solution of suppose 147 gram of H2SO4. Okay, H2SO4 has dash normality in 3000 ml solution. Okay, this is the problem. A solution of 147 gram of H2SO4 is dash normal. That is what is the concentration of H2SO4 basically. Dash normal in 3000 ml of solution. How will you solve that? So given weight is equal to how much? 147 gram, and what is the gram equivalent weight? Gram equivalent is 49 gram. So the number of gram equivalent is 147 divided by 49. Okay, this is gram, not 99. Okay, yeah, 147 divided by 49, that is 3. Now what is the value of normality? Normality equal to number of gram equivalent divided by volume in liter, volume of solution in liter, right? So this is 3000 ml, this is equal to 3 liters. So this 3 comes here, that is the number of gram equivalent. 3 divided by 3, that is 1 normal. So the answer is 1. So 147 gram of H2SO4, if it is dissolved in 3000 ml, the concentration will be 1 normal. I think the concept of normality is clear, right? And if it is not clear, you can text me on LinkedIn, or you can ask me any questions. Okay, So this is the concept of normality. Okay, so let's try to solve this problem. Okay, what does the problem state? The problem states that suppose you have a solution of hydrochloric acid HCl with a molarity of 0.5 m and a volume of 100 ml. You also have a solution of sodium hydroxide, that is NaOH. Let me just underline different color. NaOH, that is with a molarity of 0.8 molar and a volume of 75 molar. Find the resultant molarity of the solution. The question is incomplete. Find the resultant solution when, come on, write it, when these two are mixed, right? When these two are mixed, find the resultant molarity of the solution. How will we do that? Okay, so suppose this is HCl, this is the beaker where I am keeping the HCl, and this is, what is this? This is NaOH, right? This is NaOH. Okay, so I have to find, this is the resultant. We write in red, resultant, right? So for the HCl, the M1 is given. What is the M1? The M1 is given 0.5 molar. And what is the volume? The volume is 100 ml in 100 ml. Okay. And what is the M2? M2 is NaOH. NaOH is, sorry, not N, it is 0.8 molar, right? For volume, it is 75 milliliter. Okay. So now the V3 is not, M3 is not given, obviously we have to find the M3, but V3 is not given, right? But V3 will be equal to V1 plus V2, obviously, no? Because V3 is created by mixing volume 1 and volume 2, so V3 will be V1 plus V2. So indirectly V3 is already given to us. What is the value of V3? The value of V3 is 100 ml plus 75 ml, that is 175 ml, right? 175 ml. Now we have to find molarity, and from the formula we know that molarity is number of moles of solution of the solute in, like, per liter of solution, right? Per liter of solution. So we have to convert this into liter. Simply we have to divide it by 1000, and after dividing by 1000, what comes is 0.175 molar. No, like, not molar, sorry, this is liter, right? This is the total volume. Now the formula is, for, like, the concept is number of molecules remains the same. Okay, that is the concept. So the formula is M1 V1. I will just write in different because I am using rate to represent a resultant, right? So M1 into V1, that is number of moles per volume into the total volume. So what does it become ultimately? Ultimately it becomes the number of moles, right? The number of moles represents the number of molecules. So just now we saw that we can find the number of moles by, like, dividing the number of molecules provided by the Avogadro number. So number of moles is nothing but the quantification number of molecules. So M1, that is number of molecules per volume into volume, that is total number of molecules of, like, substance 1. And what is the number of molecules of substance 2? It is, sorry, this is not M2 into V2. So the number of molecules after mixing, will it change? No, it will not change. The number of molecules of each substance will be same. So, and what is the number of molecules for the, like, resultant? M3 into V3, right? So simply if we add the number of molecules, it should be equal to the number of molecules of this one. So here is the, like, formula that comes is M1 V1 plus M2 V2, this is not V, this is some, like, gamma or something, V2 is equal to M3 V3. Done. This is the formula, right? So if we apply this formula to our given question, then what is the resultant? The resultant is not that, yeah, so if you plug in the values, that is 0. So V3, what is the value of V3? V3 is M1 V1 plus M2 V2 divided by V3. Now let's plug in the values. 0.5 into 0.1 and plus 0.8 into 0.75. Why it is 0.75? Because I'm writing it in liters, right? What is the value? 100 ml and 75 ml. I think 0.075 will be the right one. 0.075. Okay, and divided by 0.175. If you just plug this into the calculator, the answer will be, I don't prefer calculator actually. 0.5 into 0.1 is 0.05. Sorry. Yeah, 0.05 plus 0.8 into 0.075. You can consider 0.75 as 0.08, and 8 squared is 64. So it will be very close to like 0.064. Since it is 0.064, we can just ignore the 4 and it will be 0.06, right? Divided by 0.175. If you do the maths, then it is equal to 0.11 divided by 0.175, and it will be very close to 0.62. That is, the answer is 0.62 molar. That is the answer of this question. That is, the resultant molarity is 0.62 molar, and 0.62 is like 0.6. So this is the answer. Okay. I think this part is clear. Okay, so now let's dive into the pH, pK and the buffer concepts. That is the Henderson-Hasselbalch equation. Okay, so let's start. Okay, Henderson and Hassel. I think you should remember this like spelling also. Most of the students I have seen, they like mess up in the spelling of the Hasselbalch equation, right? Okay, so this is the equation of like acid, base and weak. This is the mainly equation of weak acid and weak base, and calculating the pH of weak acid and weak base. And you can also use this to calculate the like degree of protonation and degree of deprotonation of a weak base or weak acid. Okay, so what is the concept? The concept is HA is our acid. Suppose HA is our acid, and when it dissociates, okay, so if it is a weak acid, we will just use this reversible form like arrow to make it more chemically correct. Okay, if that makes sense. So acid will dissociate into hydrogen ion and A minus, right? So the pH is equal to pKa, A for acid, okay, A for acid, and this is a like dissociation constant. This every reaction has a dissociation constant. So this is the dissociation constant of the acid. So this is the pKa. And what is P? I will just tell you in the moment. So pH is equal to pKa plus log concentration of A minus divided by the concentration of HA. That is, what is A minus? A minus is the deprotonated form, deprotonated, and this is the protonated. So pH is equal to pKa plus log of deprotonation by protonation, right? Okay, so what is pH and pKa? Okay, so P of anything is equal to minus log of concentration of that thing. That is, if we just write, not rate, it is not that important, this is giving you a concept. Okay, so the pH is equal to minus log of concentration of H or H plus, okay, H plus, and so pKa is equal to minus log of Ka. There is a dissociation constant of acid. Similarly, there will be a dissociation constant of base also. So pKb is equal to minus log of concentration of Kb. Okay, Okay, so this is the concept of P, that is minus log of something, and minus log of concentration of something, that is the P of that element. Okay, so the concept is like this is the Henderson-Hasselbalch equation for acid. So what will be the counterpart for the base? It is like very similar to this one. A plus base will accept H plus N, right? So A plus H plus is equal to A. You can like imagine this like NH3 plus H plus is NH4. This is like more biology into it, right? We see this reaction in many biological reactions, like even in the amino group, that is in lysine. At a certain pH, it becomes the epsilon amine group becomes NH4 plus, right? Okay. So the what will be the formula of finding the POH? Similar to that one, P of pKb, it will be the like dissociation constant of base, right? Constant, let me write it better. pKb plus log of, what do you think? What will happen? What will be in the like denominator and upper value? What is that called? Numerator, right? What will be the numerator and denominator? Again, it will be NH, that is A plus divided by A. Okay, like it is a very good way to remember that. Again, it is the like division of the concentration of the product divided by the substrate. The only difference is that we are in the product section, we are not multiplying the hydrogen ion concentration, right? So this is like the the fraction or the like division, like ratio, right? Ratio is the correct word I am searching for. The ratio of deprotonation protonation. For POH, this is the formula, and for acid, this is the formula. We'll just solve a question to understand it better. So from this concept, if A minus concentration is equal to HA, right? If A minus is equal to HA, what will happen? pH will be equal to pKa, right? From this equation, if this is equal to this, what will happen? This will cancel out to be 1, right? And what is the value of log 1? This is why we need to learn the value of logs also. What is the value of log 1? Anyone? The log 1 value is 0, right? When this part is 0, so pH is equal to pKa, because this part is 0, right? Okay. So when A minus is equal to HA, then pH is equal to pKa. Okay, so when the concentration of A minus is greater than HA, that is the acid, that is the deprotonation form, the concentration of deprotonated form is more than the protonated form, what will be the pH? The pH will be greater than pKa. Why? Because the numerator is greater than the denominator, so this is the positive value, log positive value. So pH is equal to pKa plus positive of something, right? So pH is greater than pKa, simple logic. And similarly, if you reverse this section, like reverse this relation, if this is less, then similarly this will be the denominator will be greater than numerator, so log this part will be negative, so pH will be pKa plus something, minus something, because if denominator is greater than numerator, then log becomes a negative value, so pKa minus something, so that is pH will be less than pKa, right? So this is like common relationship between deprotonation, protonation, and pH and pKa. Okay, so let's solve this problem. So there are two ways of solving this problem. One is the general way and another is like a trick way. I will show you the trick after I discuss the general one. So let me give you some options for this question. The options are like option A is 0%, option B is like say 10%, option C is like 90%, and option D is 98%. Okay, now let's start solving the question. What is told in the question? I'm sorry. Yeah. Uh, in 100 ml of 0.2 molar CH3OH, 100 ml of 0.2 molar of CH3OH, the pKa, that is the dissociation constant of CH3OH, is given. In most of the cases, the pKa is already given. You cannot just like um, know the values by head. If the numerical needs the value of pK, it will be given in the numerical only. Don't worry about that. So 100 ml of 0.2 molar CH3OH pK is given, is titrated with 0.02 normal of KOH. Okay. After addition of the base, the pH of the solution is 2.76. So the pH is given. Let me write down the pH. The pH is given. The pH is 2.76, right? The pH is given, and the pK is also given. So pKa is 4.76, and at this point in the question, again, at this point find the degree of protonation of CH3OH. Okay, so what is the meaning of degree of protonation? Another term is there, that is degree of protonation. It is nothing but which one is the protonated form? Let me see from this one. Ha is the protonated form, and deprotonated, that is D, meaning it doesn't have, it has lost it. Decarboxylation means losing carbon dioxide, right? So deprotonation means deprotonated form, that is the like A1, A minus, sorry, not A1, A minus. So if this is the acid, this is the conjugated base, right? So the correct expression is pH is equal to pK plus log, and the ratio of conjugate base by conjugate base by weak acid, right? This is conjugate base by weak acid. I don't want to complicate things, that is why I wrote deprotonated and protonated, and I wrote A minus by Ha. But the real definition in the bookish definition is pH is equal to the summation of the ratio of conjugate base by weak acid, the log of that, plus the pK, that is the minus log of dissociation constant. I just didn't want to confuse you, so I just write A minus and Ha. So A minus is the deprotonated form. Now we have to find the degree of protonation. So degree of protonation is nothing but the protonated form, the concentration of protonated form divided by the summation of protonated form and the deprotonated form. It is very simple concept, right? What is the degree of protonation? The degree of protonation is the concentration of protonated form by total. So what is the total? The total is like the concentration of Ha, that is the protonated form, the deprotonated form. Okay, so if you plug in the values, the pH, we know the formula, that is pH equal to pKa plus log of that. So pH is equal to, that is 2.76 is equal to 4.76 plus log of, okay, so what is the reaction when this CH3OH and KOH is added? What is the reaction? The reaction is CH3, sorry, COOH, and this is dissociating it. What is happening with my pen? Yeah, so dissociating in CH3 COO minus plus H plus, right? This is what the weak acids do. So the log of concentration of CH3 COOH minus divided by the concentration, not H minus, sorry, COO minus divided by the concentration of CH3 COOH, and this part is our A minus, right? This is the concentration of A minus, and this is the HA. This is the weak acid, right? Conjugate base by weak acid. So if we subtract this one, so it becomes minus 2 is equal to log of A minus divided by HA, and like if we bring this one here, that is log. If we bring this one again, the log property comes, that is minus 2 equal to log of x. Then what will happen? X equal to anti-log of 2. So x, and here x is equal to the ratio of a minus and ha, right? So what will be x? X will be equal to anti-log of minus 2, and from the logarithmic properties we know that anti-log is not a fancy term, it is nothing but 10. Then 10 to the power minus 2 x is equal to a minus concentration divided by ha. So this is equal to 10 to the power minus 2, right? So what is 10 to the power minus 2? 10 to the power minus 2 is nothing but, this is nothing but 1 by 100. So this, let me write it clearly, this is 1 by 100, right? So what does this mean? For for ha equal to 100, a minus is equal to 1. So what is the value of ha plus 1? That is 101, sorry, 101, and we have to find the degree of protonation. We have to find the degree of protonation, right? For the degree of protonation we have to divide the ha. What is the ha? So therefore degree of protonation equal to concentration of ha. What is ha? This one, 100 divided by 101. So this is approximately near to 99%. So the answer is option D, right? Makes sense? The degree of protonation is 100 divided by 101, that is 99%. So these values, 100 ml of 0.2 molar CH3 and that is the 0.2 normal of KOH. These are like extra values to confuse you maybe. So just find the right values that you need to solve the sum and just go forward with the formula. It is so simple. Many times you will see such extra values and don't get overwhelmed with these values. Just focus on the like important stuff. Okay, I think this general way of solving this question is over. Now let's see the trick, right? What is the trick? The trick is, we know this formula. Okay, very well, we know this formula. Now let's play with this formula. So what is log a minus, I'm not just giving the like brackets, understand this means the concentration only. Okay, pH minus pKa, right? So it can like have three different like types, three different scenarios. The scenarios are where the pH is equal to pKa, pH is equal to pKa. So what will happen? This part will become 0, right? This part will become 0, and like then what will be the like anti-log of 0? That is 1. Why the anti-log of 0 is 1? Because the log of 1 is 0. So anti-log of 0 is 1, and when it becomes 1, the a minus is equal to ha, right? The concentration of a minus is equal to ha, that is 50% dissociation. 50% is in the deprotonated form and 50% is in protonated form, right? Okay, so another situation is when pH is less than pKa, right? What will happen when it's less than pKa? If in this case, if the difference is equal to 1, this is where the trick lies. If the difference is equal to 1, that is pH minus pKa is equal pKa minus pH is equal to 1, when pK is greater, what will happen? This part, right? This part, I think, one second, the pH is less than pKa. In this question also it was pKa is 4 point, yeah, right. So when pH is less than pKa, and so this part becomes minus 1, and what is the anti-log of minus 1? That is 1 by 10%, right? So 10% will be concentration of A minus, 90% will be the concentration of HA, right? This is the ratio of deprotonation and protonation, and when the difference becomes 2, same 1 by 100, right? 1 by 100. So the A will be 1%, and A minus will be, concentration of A minus will be 1%, concentration of HA will be 99%. Okay. Okay, great. This is the trick. So as you can see that in our given problem, the pH was 2 and the pK was how much? pK was 4.76, so difference was only 2. So from this step only we could have solved the whole problem by using the trick. So what is the trick? When the difference is 2, the concentration of A minus will be 1%, HA will be 99%. That is the protonation, degree of protonation will be 99%. Okay. Okay, if the difference is 1, then the degree of protonation will be 90%. Okay, just remember the trick. Most of the numericals will find the difference between 1 and 2 only. I have seen in many PYQs also in different competitive exams, the differences are 1 and 2. So if it is 1 and 2 and degree of protonation is asked, so you can directly take the answer 90% or 99%. You don't have to waste the time. Okay. 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 Now, enzyme kinetics. This is a very important one. Enzyme kinetics. So whenever we talk about enzyme kinetics, these graphs come into our mind, right? Whenever we say the term enzyme only, these graphs come into mind. This will be like this one, will be x and y coordinate, and this will be it's not writing. Okay, it is writing. Maybe we will rub this one. Yeah. So this is reactant, and here is the product, and there will be a graph like this, right? And this is the activation energy. This is the activation energy, and there is a difference if the product is at higher level of reactant. It is known as endothermic reaction. We've already seen these things a lot of times. These are the basic things that come in our mind whenever we say enzyme, right? What is the role of enzyme? Role of enzyme is to decrease this one. That is the activation energy, right? The role of enzyme is to decrease the activation energy, and here is the reactant, and here is the product, and again this is the energy diagram. And now you can see that the product is below the reactant level, so it is exothermic reaction. So this is actually releasing energy. So this is exothermic reaction, right? And again this is the activation energy. Okay. Okay, so these are the basic concepts that we already know. Now let's dive in. So for any reaction mechanism to happen, there are three criteria that we need to consider. That is, whenever two molecules are hitting each other, they are hitting each other. So the collision is important for any reaction to happen. There are billions of molecules roaming around in a reaction beaker, and if they are not colliding, if the atom of the top of the lead, if this is a lead, in a atom on the top of the lead, this one and this one is not colliding, there will be no reaction between them, right? This is a common sense, but we need to consider this parameter when we are calculating various things. So the first criteria of any reaction is collision, right? Collision. What is the second criteria? Second criteria is orientation. This is a molecule, and this is another molecule. If they are colliding right now like this, the collision is happening, this step is done, but will they react? No, they will only react when they collide like this. Think about enzyme substrate binding. In which case, in case 1 and case 2, in which case do you think product will be formed? This one or this one? Obviously this one, right? So the orientation is also important. So the orientation is also important. I'll just remove the clumsiness of these things. So orientation is also important. Orientation, right? And another thing is very important. If some of the reactants, like again in the beaker situation, if this reactant or the reactant and the maybe this top right corner has not crossed its like enzyme like activation energy, will it be able to like form the product even if the collision is there, even if they are in the right orientation, collision is happening, will it like form the product? No, because active it has to have the energy which is more than activation energy, right? At least it has to have the energy of activation energy, right? It needs energy, like energy, right? It has to has the minimum energy for reaction, and minimum energy of reaction can be like said in these two forms, activation energy and the temperature, right? Activation energy and the temperature. Okay, so these are the three parameters for like any reaction to happen. So Arrhenius came up with this like this formula that the rate constant, it is not writing, why? Yeah, it is writing, the rate constant is dependent on all these parameters. That is, this parameter is like written in z. Z is the collision parameter, and p is the orientation parameter. Okay, so the like formula is rate constant, that is k, right? K, rate constant, is equal to, like it is constant, it is a constant, we say that rate is proportional for first order reaction, rate is proportional to the like concentration of substrate to the power 1, and that is why we are calling it first order. If it is 2, then it is second order. 0, then it is not dependent on the substrate concentration, it is 0 order anyway. So rate is like directly proportional to the like concentration of the substrate to some power. So if we equal this thing, rate is equal to rate constant into concentration of substrate to the power 1, maybe like I'm considering it as the first order, so it is this formula, right? And we say that this rate constant is constant and it is not dependent on substrate concentration. That is absolutely right. But this rate constant is dependent on temperature and collision frequency and activation energy and the current orientation parameter, that is P. So what is the relationship between rate constant and all these four parameters? That is given by Arrhenius. K is equal to Z for the collision into P for the orientation into Euler's number E to the power minus of EA divided by R, that is universal rate gas constant, in divided by T, that is EA divided by R into T. This is the Arrhenius equation. This is very important. Okay, this is very important. This is the Arrhenius equation. Great. Okay, fine. Now let's interpret this equation, right? So if EA is very high, what will be the value of this one? It will be negative, right? If EA is very high, so the reaction, what is the probability of happening the reaction? It is very low, right? The EA is very high, that means EA by RT, this value is very high. But since there is a negative term, the overall this part becomes very low, so the rate constant is very low, so the rate of reaction is very low. This makes sense. If the activation, that is why enzyme is required to lower the activation energy, so that the rate constant value is low, so that the rate of the reaction is like optimum, so that the reaction actually takes place, right? We can say that from substrate to product, if there is no reaction happening, we can say that the rate is like infinitely small, like at infinite time at infinite duration it will it will be converted to product, which is never. But mathematically we can say it is infinite, right? So if the activation energy is too high, like infinity, the rate constant will be too low, like negative infinity, and so the rate will be also in negative infinity, that is at infinite time the like reaction will occur. Make sense? Okay. So from this equation we can interpret that if like activation energy is low, the rate constant will be high, since there is a negative like sign. So if the rate constant is high, the rate will be like very high when it is multiplied by the substrate concentration, right? Okay. Now if temperature is high, what will happen? Ea by RT will be high or low? It will be low, right? It will be low. Why it will be low? Because the temperature is in the denominator, not in the numerator. So Ea by RT will be low. Again, there is a negative sign, so negative Ea by RT will be high. And when negative Ea by RT is high, so this part is high. When this part is high, K is high. So at higher temperature, the rate of reaction will increase, right? So the rate of reaction will increase, and this also makes sense. Like when the temperature is high, the collision will be more. Maybe the orientation is not perfect, but the collision will be more. And this part, the like e to the power minus A by RT, this part will be more. So the rate constant will be very high. So when temperature is high, rate of reaction is high. When the like activation energy is low, the rate is again high or fast. That is why where the enzyme comes in, it actually decreases the activation energy. Now whenever we like hear the term like enzyme kinetics, there are a few terms that comes in our mind. One is reaction, and I explained the parameters of reaction. This is done. Another thing that comes into mind is rate of reaction, and this is also done. That is, rate is equal to the rate constant into substrate concentration to the power n. If n is 0, it is 0 power, 1 is 1 power, 2 is second power of reaction. Okay. And then there is rate constant. For rate constant it is K, and the equation of K is I already told you, that is derived from Arrhenius equation. Okay. It is dependent on three parameters: collision, orientation, and energy, that is activation energy and temperature. Okay, that is the Arrhenius equation. Okay. And many times the Z and P are together, said as A, that is frequency factor. So in most of the equations, maybe in most of the books, you will see that this reaction K is equal to A into e to the power minus Ea by RT. What is this A? This A is nothing but the like multiplication of collision and orientation. That is the frequency factor. Z is collision frequency, and P is the orientation frequency, and Z into P is frequency factor. Okay. So this is also the like Arrhenius equation that you will find in most of the books. Okay. So let's like start with that equation only. K is equal to Z into P, or I will just directly write A. Okay, that makes more sense. A e to the power Ea by RT. Now we know we are like very familiar with log and ln, so let's put ln on both sides. Ln K is equal to ln A, and when it is A into something, into will be converted to plus summation n. Now summation of ln is nothing but log of base E, right? Log of base E, and there is E minus Ea by RT, right? What will be the value of this? It will be directly minus Ea by RT. Okay, we know that log of base B of B to the power x is equal to x only. Okay, we know this property by now, or even if you don't remember, just go to, I don't know, third or fourth slide, maybe the logarithmic wala side, and you can find it there. Okay, right. So now the equation becomes ln k ln k equal to ln a plus, not plus actually, this minus will come here, and this will become minus ea by rt, right? Now we can convert this part in like what is the formula of a straight line? We all know that the graph theory and the formula of a straight line is y equal to mx plus c, and what is y? That is the like y coordinate and the x coordinate, and the m is the like slope of the curve, and c is the y intercept, right? Y c is called the y intercept and not the x intercept, because in this equation if x equal to 0, x equal to 0, y equal to c, so this is the y intercept, not the x intercept. Okay, just basic things. Okay, so in this equation I can see this, I can put this as y, and I can like put this part, actually this part as m. So this is minus m into x. What is x? X is 1 by t, right? 1 by t is x, this part is c. Let me rewrite this, like rearrange this equation so it is more clear. Ln k equal to minus ea by r into 1 by t plus ln a, right? Now it is like more obvious, right? This is y and this part is m, that is the slope, this is x, and this is c. Now we can plot the graph. It is very easy to plot the graph. I think I will do it in the next page maybe to avoid complication. No, there is some okay, I will just add one more page. 1 second. Which one? This one. Edit, add, and duplicate. Which one has been duplicated? Oh no. Okay. Come on, where are you? Okay, I think yeah, this is the duplicate one, and I will just take it here. Done. Okay, so this is the y and the m and the x. I will draw the graph now. Sorry for the delay. This is y, this is x, and this is x, this is y, and what will be the graph? The graph will be like this, and the y dashed, just give a solid one. Yeah, right? So what is the y-intercept? The y-intercept is c, and what is the c? Let me see the c. Sorry, bad joke. Yeah, what is the c? ln a, right? ln a, this is the c, that is the y-intercept, and like what is the m? m is this is the slope. What is the m? The m is minus ea by rt, right? And what is the x? X is 1 by t, and what is the y? Y is ln x. Very often you will find this like this graph, and this is a very common graph in many competitive exams. That is why I am showing you this, and not only that, you have to solve many numericals from this graph also. Okay, so what is this r I am talking about from that point? Like r is the universal gas constant, right? Universal gas constant, UGC. Yeah, so universal gas constant, and the value of r is very important. You need to remember this. There are two values of r that you need to remember. Let me make this bigger. Okay, first one, that is 8.3145, and another is 2. Why there are two values? Because there are two different units. What is the units? The first unit is joule per mole per Kelvin. This is the unit of R when the units are given in joule and mole and Kelvin, right? And what is 2? It is not actually 2, 1.98 or something, so approximately you can consider it as 2. 2 is calorie per mole per Kelvin. When the energy is given in joule, it is 8.3145, and when it is given in like calories, you can consider R as 2. Okay, these are the two like very important values of R that you need to remember. Okay, fine. So from this equation I can say that slope is equal to minus A by RT, right? And what is the slope of any like straight line? We know that the slope is y2 minus y1 by x2 minus x1, right? And from this is again equal to minus EA by RT, right? So like y2 is, what is the y coordinate? That is ln k, that is y, right? So y2 will be ln k2 minus ln k1 divided by what is x is 1 by t, so x2 will be 1 by t2 minus 1 by t1 equal to minus EA by RT, right? Or not t, actually this is, the slope is not RT, the slope is actually R, not RT, sorry, the slope is actually R, right? The slope is actually R because 1 by t is already the x coordinate. You can see from this reaction also, the EA by R is the slope, this is the slope, this is the x coordinate, this is the slope, EA by R. So in this also minus EA by R is the slope, and slope is minus EA by R, and these are the formulas. So from this equation I can say that whenever ln k2 minus ln k1, I can write it as division, right? Ln k2 divided by, not minus, divided by k1 from log properties, we know that. Okay, so like this minus, if we like bring it this side, the t1 and t2 will be changed, reversed, 1 by t1 minus t2, 1 by t2, and now the minus sign will not be here, r, right? Now from this equation, ln k2 by k1 is equal to EA by R into, if we just bring the denominator to this side, minus, sorry, 1 by t2, right? Very simple. And now the k2 becomes, the value of k2 is like, let me increase this one, the value of k2 is the k1 will come this side, and k1 into this ln will be anti-log, when it comes that side it will be anti-log, right? And what will be the anti-log? That is, ln means the base is e, so e to the power, this total part, e to the power EA by R into 1 by t1 minus 1 by t2. This is how you find k2, right? This is how you find k2, and you go and just play around with the equation, and you can also find like t2 equal to what and EA equal to what, right? Equal to what? Just for finding EA, you have to like put this R in that side, and you don't bring this denominator on that side, and that is how you find it EA. Okay, just play around with the equation and you will find like various like t2 equal to something, e1 equal to something, k2 equal to something. Why do we need this one? Because from the Arrhenius equation alone, you cannot find two different like k's or EA. You cannot find the like activation energy. And like, rather than like explaining verbally, I will just go to the next problem, or the next numerical. You will understand what I am like trying to say. So in this problem, it is said that a certain reaction where the activation energy is given, there is 50 kilojoule. Again, remember, it is the activation energy is given in joule, so we have to consider the value of R as 8.3145, right? Okay. So the EA is like 50 kilojoule at the and rate constant at 25 degree temperature, at 25 degrees Celsius is this one. So this is where the equation comes into life. So EA is 50 kilojoule, means 50,000 joule per mole. Never ignore the like units. Units are really important. And temperature at 25 degrees Celsius, that is T1 equal to 25 degrees Celsius, but we'll know that we have to convert the degree Celsius into Kelvin. So 273 plus 25 is equal to 298 Kelvin, right? And what is the value of rate constant at 75 degree temperature? So T2 is given. T2 is like 75 degrees Celsius equal to like 273 plus 75 is equal to 348 Kelvin. And what else is given? Okay, this is the K1, right? The rate constant at T1 temperature. Rate constant is given in 0.0039 minute inverse, right? Okay, so we have to find K2, that is rate constant at temperature T2, right? So this is where the formula comes into life. Here we can apply this K2 wala formula. If similarly K2 was given and you have to find the T1, like play around with this equation and find a formula for T2. And similarly, if activation energy E1, that is 50,000 joule per mole, it is not given, you have to find the E1 and all the other values are given. So just again play around with the equation and you will find an equation for E2. Okay, so if I plug in the values, K2 is equal to, and okay, so R is not given, but I know when the values are given in joule and mole and Kelvin, the R will be 8.3145 joule per mole per Kelvin. Okay, right. So K2 is 0.0039. Again, I will like prefer to write the units, but it is a complicated equation, so I will write the unit at the end, right? Just write the units so that you don't mess up anything. So K1 and then e to the power, like e to the power, like we have to write the big formula now, 50,000 divided by, what is it, 8.3145. If you consider the like units, 8.45, that is joule per mole per Kelvin, and in the upper that is joule per mole, so it is only like Kelvin. And for here 1 by T2, 1 by T1 minus T2, right? I think, yeah, right, 1 by T1 minus T2. T1 is 298. Let me zoom in. 298 and just remove this. Yeah, so 1 by 298 minus 1 by T2. T2 was 348. Okay, so 348, right? And this is Kelvin, and here it was Kelvin, here Kelvin inverse, it was Kelvin, so it will cancel out, and so the remaining unit will be in minute inverse. Okay, so just if we plug in these values, I can bring the minute inverse nearer, closer. Oh no, it's not allowing me. Okay, I'll just rewrite it. This is the value. Come on, write it. Minute inverse. Okay, so if you plug in the value, what is the value? It comes approximately like 0.0708. So does this make sense? Let me see. The T1 and T2, which one is greater? T2 is greater. From Arrhenius equation, which should be more, K2 or K1? Obviously from Arrhenius equation, if the T2 is greater, EA by RT is small, but negative EA by RT is greater, so K2 should be greater than K1. Let me see, what is the value of K2? K2 is this, and where is K1? K1 is this. So we can clearly see that the value of 0.07 is greater than 0.004 or 39. So K2 is greater than K1. So it makes sense, complete sense, right? And what is the unit of this one? Minute inverse. Okay, this is how you solve numericals like this. I think this part is clear. Okay, now let's go to enzyme kinetics. Enzyme kinetics. Whenever we talk about enzyme kinetics, one very common graph comes into our mind. This one, right? And we all know this is the like half of the Vmax, and this point is the like Vmax. I will decrease the thickness. Yeah, this is Vmax, and this one, this y coordinate, this represents the velocity, and this represents the substrate concentration, right? The x represents the substrate concentration. Okay, and another thing that comes in our mind is the Michael-Menten's equation, right? Michaels-Menten. There are two names, Michaels and Menten. Do you have any idea who Menten was? There are very few instances where we like Marie Curie and everything. So women in science, we do not like see very prachar about that, right? So we study about Michael Menten, but very few of us know that Menten was actually an woman. So hats off to her. And the equation is V0 equal to Vmax into substrate concentration and Km plus substrate concentration. This is the Michael-Menten's equation. We all know that. And this is the Michael-Menten's plot. And from this plot, it is very hard to like interpret anything other than Km and all. Okay, so what is this point? What is this x-intercept? The x-intercept is Km. And what is Km? I will explain. I think everyone knows, but still I will explain. Okay, so from this graph we cannot interpret like many data, so we have to play around with this equation, and we know that this gave rise to the double reciprocal plot, right? Double reciprocal plot. So let's write the reciprocals. 1 by V0 is equal to Km plus S by Vmax. I will just write Vm to save time. Vm by S, right? So 1 by V0 equal to, if we divide the like both Km and S by Vmax by S, it will become Km by Vmax into 1 by substrate concentration, right, plus 1 by Vmax. So again, if this is our y, this is our m, this is our x, this will be our c. Now we got the equation y equal to mx plus c, right? Y, come on, right, yeah. So what is happening? Y equal to mx plus c. So let's plot the y equal to mx plus c. Y equal to mx plus c, this one and this one, and this is y equal to mx plus c. And what is the m? The m is, let me just change the thickness. Yeah, so the m is the slope, that is Km by Vmax, right? And what is the like x is concentration of the, not like this actually, 1 by concentration of the substrate. And what is y is 1 by V0, that is the velocity. And what is the y-intercept? That is c. What is c? C is 1 by Vmax. And what is this intercept? How to find that intercept? It is very easy. Just at this point, what is the value of y? The value of y is 0. In this equation, that just put the value of y equal to 0, and you will find the value of x. If we, let's do that actually. So 0 equal to, what will be the equal of 0 in this equation? 0 equal to Km by Vmax, and what is 1 by x? This is x. We have to find the x. 1 by Vmax, right? So if you bring Vmax 1 by Vmax this side, you will be negative 1 by Vmax equal to Km by Vmax into x. This Vmax gets cancelled and Km will come this side. So just if we reverse the equation, x will be equal to minus 1 by Km. Simple, right? So this point becomes minus 1 by Km. Okay? Okay, done. So this graph is known as the famous double reciprocal plot, right? This plot is known as double reciprocal plot. We know all these parts. So just let me quickly say what is the like Km. Km is nothing but the concentration of the substrate. Where did my Km go suddenly? Km, yeah, it is here. So let me rewrite this. So the Km is nothing magical. It is just equal to the substrate concentration where the V equal to Vmax by 2. This is what Km is nothing but no magical thing, nothing. It is not a new parameter. It has the same unit as substrate. So it is the concentration of the substrate. Always remember, Km is not a new thing. It is not a some constant that came up from the cloud. It is just the concentration of the substrate. Km is the concentration of substrate at which the velocity of the reaction is Vmax by 2. Okay, what is Vmax? What is Vmax? Vmax is the maximum velocity. Maximum velocity. Why there is a maximum velocity? Because the number of enzymes is constant. If you make the total number of available enzyme constant, then there will be a certain velocity of the reaction which it cannot cross, right? If all the enzymes are busy, how the reaction will proceed further than that? That is the saturation point, right? If you give 1 billion substrates and there are only 10 enzymes, so 10 products per second will be the highest rate, right? Maybe not per second, maybe per millisecond or microsecond, whatever it is. If you make the time constant, then the velocity will be saturated after time, right? This is the saturation point where so this is the saturation point where if you increase the substrate concentration to a billion or a trillion or whatever it is, the velocity will not change. It cannot change because all the enzymes are saturated. Substrate cannot magically get converted to product because there is no more velocity. So what I'm trying to say is Vmax is directly proportional to the concentration of the total enzyme that was present before the reaction, right? Let me just write it clearly. Yeah. So Vmax is a property of the total concentration of the initial enzyme. Okay. Vmax is the Vmax. This is very important. I just explain you in the next slides, few slides, why it is important. Vmax is a property of concentration of the total enzyme, right? Okay. And there is also an a relation between Vmax and Et. If you just remove this proportionality, it will be a constant, and the constant is known as some of you might know, this is K cat. It is also known as the turnover number, right? Number. So the equation becomes let me reduce the thickness, and then the sorry, one second. Then the Vmax is equal to K cat into concentration of E into T. Okay, turnover. Okay, so this is the reaction. What is the take home message from this equation? The take home message is Vmax is a property of the concentration of the total enzyme present before the reaction was started. Okay, so that was the key concept. So let's start with inhibitions. Okay, so another one that I need to tell, that Km also determines the affinity. Like if half of the Vmax is reached at a like lower substrate concentration, if there are two like substrates, substrate 1 and substrate 2. So in this scenario, if substrate 1 takes like 2 micromolar concentration, at which Vmax by 2 is reached, and substrate 2 takes like 10 10 micromolar concentration to reach Vmax by 2, right? To reach the same like velocity. Come on, yeah, to reach the same velocity. Which one has which like enzyme has more affinity to which of the substrate? What do you think? So if less substrate can reach Vmax by 2 than the S2, then the affinity towards S1 is more than S2, right? The very less amount of substrate is required to reach Vmax by 2, right? So whenever there is a S1, the enzymes are ready to take it up, and whenever there is S2, it will like, okay, yeah, I will take it, let more of them come, right? So that is the affinity. So like if you like try to become S1 in the job market also, so that the affinity of the job seekers is higher towards you, like learn the skills, learn the market ready hands-on skills in biology, so that you become the S1, right? The affinity of the market, that is the enzyme, is more towards you whenever you are in the market and everyone wants to take you up. And don't be S1 like ठीक है मैं कर रहा हूँ सीख लूँगा बाद में. So the market will be like 10 of them, let them come and I will just pick one or two. So don't be S2, always try to be the S1. Okay, so take home message was Km is inversely proportional to affinity. Affinity what? Affinity of the enzyme towards the substrate or the substrate towards the enzyme. That is the affinity. Km is inversely proportional to affinity. So from this slide, like I think there are two take home message. Take home message matlab you should remember this, that is Vmax is a property of concentration of the total enzyme, and Km is inversely proportional to affinity. Okay, these are two things that you need to remember. Fine. Now in terms of plots and enzyme inhibition, there are three kinds of enzyme inhibitions, namely I'll just come to this photo or the image later. Let us discuss one by one. Okay, so first inhibition is competitive inhibition, right? Competitive inhibition. What happens? We all know all these things, right? So what happens in competitive inhibition? Inhibitor will compete with the substrate, right? So E plus S always forms ES and then product, right? But in competitive inhibition, I, that is inhibitor, will try to bind with the enzyme and it will form EI. I think I should give like reversible, all of these reactions are reversible. Okay, anyway, so it will form EI and EI will not form any product will be not formed, right? So it will compete with the enzyme itself, right? So the inhibitor is competing with the substrate to bind with the enzyme. So the binding site of the inhibitor is the enzyme itself and it is the active site of the enzyme. If this is the enzyme and suppose this is the like active site of the enzyme, the substrate will try to bind here, the inhibitor to bind here, and there will be a competition, right? So this is known as the competitive inhibition. Okay, so then again there is a new reaction that you can see, this one, this one is the new reaction, right? So I'll just remove this. This one is the new reaction where enzyme is like adding with the inhibitor, and whenever there is a new reaction there will be a new rate constant, that is Ki. Ki is the like there is Km and there is Ki. Ki is the rate constant at which the inhibitor is binding with the enzyme, right? So this is the Ki, and there is another term that I need to remember. Okay, this is not I, by the way. This is just my pen not functioning properly. Okay, so what is Ki? And there is another term that is alpha that you need to remember. Alpha is equal to 1 plus concentration of I by Ki. Okay, what is alpha? Alpha is like the main concept of alpha is never less than 1. That is, the inhibition is never less than 1. You will also learn this in like Lotka-Volterra model of inhibition. Maybe I will teach sometime, but the point is the alpha is 1 plus I by Ki, and it is never less than 1. Okay, so this is the concept of alpha, and in competitive inhibition, inhibitor competes with the active side of the binding of enzyme. Okay, so now there is another one, that is uncompetitive inhibition. And what happens in uncompetitive inhibition? That is E plus S. ये reaction तो होना ही है, बस E plus S equal to ES, then it will be product, like product plus enzyme, तो anyway whatever. So ES is becoming the product, and then the inhibitor will bind with the enzyme substrate complex. You can remember like uncompetitive as being like too pathetic in terms of substrate binding concentration. Like if the substrate has already like bound with the enzyme active site, then the inhibitor coming and saying no, I will not allow you to form the product. It is like it has already done the hard work of like aligning itself perfectly, colliding with the enzyme, and it is also like pass the enzyme energy barrier, and then the inhibitor is coming and saying like no nahi bhai, I will bind with you and I will not allow you to form any product. This is like, you can remember like this also. It is a pathetic one where ASI, that is the enzyme substrate inhibitor complex, is formed and product nahi banega, not formed. Okay, so then again there is another reaction, so there will be Ki also, but this is denoted as the Ki, so this will be Ki dash. Okay, let me write it clearly. This will be Ki dash, and so similarly there will be one alpha dash equal to 1 by the inhibitor concentration by Ki dash. Okay, this is the alpha dash. Now there is mixed. Mixed is so simple that the term itself tells everything. Mixed means competitive plus uncompetitive, right? So this is enzyme and this is substrate. Come on, this is substrate, this is enzyme substrate complex, and this is the product. What will the inhibitor do? Since it is mixed, it can also bind to the enzyme and form non-functional enzyme inhibitor complex, right? Or it can bind with the enzyme substrate complex and it can form the ESI, that is enzyme substrate inhibitor complex, and it will not form any product. Okay, so for this reaction it will be alpha and it will be Ki. For this reaction it will be alpha 1 and Ki 1. Okay, okay. By the way, what is the Ki and Ki1? Ki is equal to the concentration of the product, that is EI complex, divided by concentration of enzyme and I, right? And Ki dash is equal to concentration of the product, that is enzyme substrate inhibitor complex, divided by what is there? Divided by ES and the concentration of inhibitor. Okay, this is the EI Ki. So this is the concept of competitive, uncompetitive and mixed inhibitions, and there are two key concepts that you need to remember. The key concepts are, whenever inhibitor is binding, do you think Vmax will increase at any point of time? The maximum velocity cannot increase na, तो अगर वही होता तो we could have like added inhibitor to every enzyme reaction to increase the Vmax. So Vmax cannot increase, right? And Again, Vmax is a property of total energy, that is the total concentration of the enzyme, as I told you in the previous slide. So by in adding inhibitor, the Vmax is not changing. So the Vmax can only the Vmax, the concept is Vmax will never increase, right? So Vmax can decrease or stay constant, right? Constant. But for Km can increase or stay constant, or it can decrease. Now you will say that decreasing Km means affinity will increase, and if affinity is increasing, then we should add inhibitors to increase the affinity of substrate to like enzyme. Like if you are designing a drug, we should also like inject the inhibitor of the drug so that the affinity will increase, right? No, the concept is slightly different. I will explain in the like next slide. Okay, so the two the three take home messages are for from this slide are: Vmax can never increase. It will either remain constant or it will decrease. Second is Km will increase or remain constant or decrease. And there is another term that will be like affecting our Michael-Mendel's constant equation, or the double reciprocal plot equation. That is the alpha term. Alpha is never less than 1, and alpha is equal to 1 plus, that is the concentration of inhibitor, by the dissociation or association constant, that is of the binding of energy with the not energy, binding of inhibitor with enzyme or enzyme substrate complex. Okay. Okay, so for competitive, non-competitive, and uncompetitive, so like for now the non-competitive is, I just told you, as mixed, because a special case of mixed inhibition is known as non-competitive. I will come to that later. So for this one, you can also think of it as mixed inhibition, right? So for mixed inhibition, like in most of the cases, like you have to memorize that Vmax is unchanged and Km is increasing for competitive, and for non-competitive this is happening, and for non-competitive this is happening. But I don't like to remember things like that. I always make mnemonics or something, so I'll just teach you like how to remember this with a mnemonic. Okay, so just like for now, forget these things. Don't focus on that one. Focus on the double reciprocal cross graphs. Okay, so suppose there is like two people standing here. There is one people, bear with me with the diagrams please. There is one people and he has a sword in his hand. Okay, he has a sword in his hand. And there is another people, he also have a sword in his hand. Okay, so what does like this picture tells you? Like if you look at this one time, you will think that these two are fighting, right? These two are fighting fighting with each other. These two are fighting with each other. Fighting means they are competing with each other, like competing with each other. So I just like to remember like this: whenever there is a graph which is like competing with each other, you will see that it is crossing at a certain point, it is crossing in the middle. You will feel like there are two swords cutting each other, right? There are two swords cutting each other. So this is competition. They are competing with each other. They are competing with each other, right? So this is competitive inhibition. This type of graph is competitive inhibition. Okay, now uncompetitive, I will come to the like Vmax and Km in a second. Just bear with me for this one. So competitive inhibition, you got it. Like I think you will never forget what is the graph of double reciprocal plot of competitive inhibition. It is competition, competing with each other. Okay, for uncompetitive, I will write uncompetitive. I will write the U like this, like this. This is U uncompetitive, right? So if you can remember that uncompetitive, here there are two parallel lines in the U. Like these are the silly ways you can remember, but this works. Trust me, in the exam hall or on the stress, these things you will never forget. So if you consider the two parallel lines of uncompetitive U, so Uncompetitive, the double reciprocal plot will be lines that are parallel to each other. This one is here, and then like this one is here, so these two are parallel to each other, right? So parallel, uncompetitive. Un, here is the thing, and then uncompetitive inhibition, right? And same thing for in. How do you write in? Like this, right? In, if I just like take this one and rotate it, I don't have a rotation option, but if I rotate it, how will I write it? Like this, and now I rotate it like this, and I further rotate it like this. The concept is just focus on these angles, like right, these angles. You can find this angle in this diagram also. Okay, so just like this, you will know that for this reaction, this is non-competitive reaction by these angles of the end. You can like think this as the angle of an N, and these two parallel lines as the parallel lines of U, and these two graphs, they are competing with each other, so this is competitive inhibition. Now I told you that this is like the mixed inhibition, this is like the mixed inhibition, and a special case of mixed inhibition is competitive inhibition. So what happens in mixed inhibition, the like point of merging is not here, they will merge somewhere like this. Okay, they will merge somewhere like here, so the like graphs will be like this only, this or this will be the point of merger for mixed, but for simplicity I am just dealing with the non-competitive, and for non-competitive it will be like this, and remember this angle from in. So this is the graph of non-competitive. Now the y coordinate represents the value of 1 by Vmax, right? So in non-competitive, the value of 1 by Vmax is changing or not changing? It is not changing. If the value of 1 by Vmax is not changing, then Vmax will not also change, right? So for competitive, Vmax, sorry, not Vmax, Vmax remains constant, right? Correct? Okay. So the Vmax remains constant, and the Km, so 1 by Km, like let me show you why 1 by Km. There is a lot of confusions in like many discussions, so students have seen that 1 by Km is decreasing, or like Km is decreasing or not. So at this point, okay, at this point, come on, yeah, at this point maybe the value is -2. Okay, maybe like I'm not scaling it up, maybe it's -2. At this point it is maybe -3. Okay, so this is like km1, this is like km1, this is for km2. So 1 by km1 is equal to -2, right? And what is 1 by km2? It is -3, right? So now what is the km1? Km1 equal to 1 by -1 by 2, and what is -1 by 2? That is -0.5. and what is km2? Km2 is -1 by 3, and what is 1 by 3? -0.6667, right? So which one is greater, -0.6 or 0.5? Obviously -0.5 is greater than -0.6. Since it is negative, the smaller number is greater, right? We all know that. So the km1 is greater than km2. So no more confusion that the km1 is greater than km2. Now let's see, this is km1, and always remember the upper line in two graphs, the upper line is always inhibited, the upper one is always inhibited. Okay, the upper one is always inhibited. So for competitive, if like same color graphs are given, don't get confused, the upper one is inhibited. In non-competitive also same color graphs are given, upper one is inhibited, and uncompetitive also upper one is inhibited. Okay, so upper one is km. Now we can see that km is greater than k2, so km is increasing when inhibitor is given, right? So this is how you don't have to memorize anything. You just close your eyes and remember for competitive those two lines are like intersecting at 1 by Vmax. Vmax is not changing and Km is changing, and like it is coming towards 0, so it is like increasing. Okay. So Km is increased, Vmax is unchanged for competitive, right? Now same thing for now, you can see that N is diverging from 1 by Km, so 1 by Km is not changing, so Km will not change. So for non-competitive inhibition, Km is not changing, Km remains unchanged, but Vmax is changing. Now you have to think, okay, 1 by Vmax is going up and down, so what will be the like resultant? Don't think so much. We know that Vmax cannot increase, right? So it has two options: either it will be constant or it will decrease. Now I can see that there is a change in 1 by Vmax, so there is a change in Vmax. So only option that it has, it cannot be constant because I can see there is change. The only option is Vmax is decreasing. So yeah, the Vmax is decreasing. Whenever there is a change in y-intercept, the Vmax is decreasing. Just close your eyes and say that Vmax is decreasing because it cannot increase and there is a change, so it must be decreasing. It's very simple. So if you close your eyes and imagine n, the angle of n of non-commutative inhibition, so the Vmax is changing. Yes, the Vmax is changing. It must be decreasing, and it is diverging from Km. So Km is not changing, right? This is the thing for non-competitive. And for uncompetitive, okay, it is parallel. So Km is also changing. So Km is going away from 0. So Km is decreasing. See, Km is decreasing, and Vmax is changing. Again, if it is changing, it can be constant. So changing means Vmax is decreasing. So it is decreasing. See, both Vmax and Km is decreasing, right? Just close your eyes and think. So it is very easy, like that only. So if I go to the next slide and just recap what I just said. So here this is when the substrate is there, and then this graph is given to you. Just close your eyes and think that, okay, this is like the angle of n. For angle of n, it is diverging from 1 by Km. So 1 by Km is not changing, so 1 by Km is constant. So Km is constant and 1 by Vmax is changing, but Vmax can only increase or stay constant. It is not constant, so Vmax must be decreasing, and it is like the corner of n. So n means non-competitive. This is the graph of non-competitive, and for non-competitive, Km is constant and Vmax is decreasing. Okay, you can just like intuitively tell all these things right now. Okay, now let me bring back those fancy looking graph. One second. This and this, and this is when substrate is there, and now it is parallel. Okay, so parallel means u, the first letter, the u two lines are parallel, so it is uncompetitive, and the Vmax is changing, so it must be decreasing, and the Km is changing, but it is going away from 0, so it must be decreasing. So it is it is a graph of uncompetitive inhibition where Km is decreasing and Vmax is also decreasing. Simple. Similarly, if I like do this one, again close your eyes and think those two lines are competing with each other, but Vmax is not changing, so Vmax is constant and Km is going towards 0. So the this must be competitive and the Km must be increasing, right? Okay, very good. Now let's dive a little deeper into this. So whenever I'm saying that Vmax is decreasing, so what is the apparent or the new Vmax in like Leninger or void, maybe void and void? You will find that they are writing Vmax, and in the upper section there is written apparent, APP, apparent. I think it is in void and void only. Okay, so the apparent Vmax after decreasing will be Vmax divided by alpha. This is where the alpha terms comes into play. The alpha is what is the value of alpha? 1 plus concentration of I divided by Ki, right? So this is the apparent value of Vmax, and whenever I am saying that Km is decreasing, it will be Km divided by alpha. Whenever I saying that Km apparent is increasing, it will be alpha by Km, right? Now where is alpha dash or ki dash? Just you will see that. Okay, so when is km increasing, right? When is km increasing? Again, close your eyes. You can see that in competitive inhibition the km is moving towards the zero, so km is increasing. And what happens in competitive inhibition? In competitive inhibition, there is a concept of alpha, right? In the, like, okay, let me zoom it. Okay, so in competitive inhibition there is a concept of alpha, not alpha dash. There is alpha, so the km apparent will be alpha into km. Okay, for uncompetitive inhibition there is a concept of alpha dash, right? Alpha dash. And in uncompetitive inhibition we can see that, and even we don't need to see at this point, we can just remember that km is decreasing and Vmax is decreasing, so this will be km by alpha dash and Vmax by alpha dash. Okay, alpha dash. Okay, so this is the apparent change in maximum velocity and km. Now let's rewrite the equations for, like, three of them, that is km and that and that. That is for competitive. For competitive, the reaction becomes what? V equal to the competitive Vmax is changing. No, Vmax is not changing. So Vmax into S divided by km is changing. Yes, it is increasing. Yes, by what factor? Alpha. Okay, so alpha km plus substrate concentration. For uncompetitive Vmax is changing. Yes, for uncompetitive Vmax is decreasing. Yes, by what factor? Alpha dash. Okay, so my pen is not working. 1 second. Okay, so it's off. Yeah, so Vmax into substrate concentration divided by alpha dash by km is increasing or decreasing. Okay, it is going like away from zero, so it is km is decreasing by alpha dash, right? Okay, and here is the substrate concentration. Like, we can simplify it also. That is the alpha dash will upper alpha dash will come down, and this alpha dash will, like, go up. So V max into S by km plus alpha dash into S, right? Yup, this is the final equation of uncompetitive. And again, for non-competitive, or I will rather say mixed in this case. Now right now I will show why uncompetitive is a special case of mixed right now. Okay, so for mixed, what happens is, for mixed, as I told you, both things will happen. The competitive and uncompetitive will happen. So what is the, like, k apparent for competitive? K apparent for competitive is this one. What is the k apparent for uncompetitive? This one. So the km apparent for mixed will be alpha by alpha dash. Both of the factors will affect alpha and alpha dash. Alpha will try to increase the km and alpha dash will try to decrease the km. That is why this is known as mixed, right? And what will happen to, like, Vmax? Again, the Vmax is decreasing because, yeah, you can just close your eyes and remember, right? So Vmax is decreasing by what factor? Again, alpha. Okay, so it will be Vmax into S divided by alpha and divided by alpha dash, sorry, by alpha km by alpha dash plus S, and you can just simplify it, and it will be V max S by alpha km. Okay, it's really bad. I'm writing km plus S into alpha dash. Okay, this is the value of mixed. Now, when does mixed becomes non-competitive? The only time mixed becomes non-competitive is when km is equal to km apparent is equal to km, right? Km apparent is equal to km because km is not changing in non-competitive. When is this possible? When alpha is equal to alpha dash. What does it mean? Let's see. 1 plus concentration of I by Ki equal to 1 plus concentration of I by Ki dash, right? This is the meaning of same, and this goes, and then I goes. So the Ki dash equal to the concentration of, that is the this. So the concept is, in mixed inhibition, whenever the association or the dissociation constant of inhibitor and enzyme substrate. Okay, what is like this one? Let me write this down. ESI by ES into this equal to EI divided by into I, right? So E gets cancelled. So the concept is ESI, concentration of ESI is equal to concentration of EI into ES by I. So what does it depict? It depicts that whenever the association or dissociation constant of inhibitor with the enzyme or the enzyme substrate complex. Okay, so what does this Ki dash represents? It represents the association constant or the dissociation constant of inhibitor with enzyme substrate, and Ki represents the association dissociation constant of inhibitor with enzyme. Whenever these two like constants are equal, then alpha will be equal to alpha dash, and in this case only Km apparent will be equal to like the Km, and in this condition, when Km is not changing, mixed inhibition becomes what? Non-competitive, right? Mixed inhibition becomes non-competitive. So for non-competitive, the equation will be Vmax into S, and like both of them alpha dash and alpha will be equal, so we can take alpha common, Km plus, okay, this will be the like equation of non-competitive, right? Great. Okay, so we have covered all this concept. I don't think there is any confusion here, and again, if there is confusion, you can ask me. Okay, so the another way of looking into these things, and I think like we can spend a day about talking about enzyme and enzyme inhibition, and I think we should spend a day about talking about this, because like most of the papers that are coming out right now is focused on drug discovery and everything, immunology, and every drug discovery needs to like pass the inhibition test or these things. So all of the new upcoming papers are focused on inhibitory study of drugs, right? So enzyme inhibition is like the greatest hottest topic right now in biology, biotechnology, or even bioinformatics also. Okay, so I think we should spend a day like talking about enzyme and enzyme inhibitions, and these concepts of graphs and like these equations and how they are changing with in the presence of enzyme, what is alpha and everything. These concepts are really important. That is why I'm like focusing too much on in this part. Okay, so the concept is, in competitive in competitive does the ET change? Does the total enzyme changing? Does it change? It doesn't change, right? It does not change. So what will happen? Vmax will change. Vmax will not change, will be remain constant. Why it is not changing? Because in competitive with enzyme, the inhibitor is binding, but remember this reaction is very reversible, and that is why it is known as competition. It is not hijacking, it is not taking the once it is binding with the enzyme, it is not taking the enzyme away from it, right? It is very like like reversible. So that is why the total pool of enzyme is not decreasing, and that is why Vmax is constant, right? But now since the Vmax is constant, but like when from I think from the like eyes of the enzyme can see there are two things: there are substrates and there are inhibitors. Like before inhibitor is added, enzyme can see only substrate. There is all substrate. But whenever the inhibitor is coming, they're like, oh, substrate is less than normal. There are more inhibitors. So in the eyes, in the field of vision, if this is the enzyme, in its field of vision, you can say that pehle there were like 4 to 5 substrates, but now in the field of vision, like there are substrates also. Now there are 4 to 5 substrates also, but now in the field of vision there are many inhibitors. So it's like from enzymes field of vision, the substrate has decreased somehow. It cannot see so many substrate, like, right? So for the enzyme to drive the enzyme plus substrate to enzyme substrate and then the product, this takes more enzyme to reach the Vmax. So it takes more like substrate concentration to reach the Vmax by 2. What does it mean? If more substrate concentration is needed to reach the Vmax by 2, that means one thing only, and that is Km is increasing. This is why the Km increases and we interpret it as affinity is decreasing. Why Km is increasing? Because more number of substrate is required to reach Vmax by 2 for competitive inhibition, right? Perfect. So for uncompetitive, what is happening? Uncompetitive, it is happening that it is binding to the ESI. And the concept is that whenever it is binding to the ESI, the enzyme pool is like decreased. Once it is binding to the ESI, this total complex becomes like useless. So from the total pool of enzyme, whenever I is binding, the ESI part is like getting vanished from the total pool of enzyme, right? So when there is a decrease in the total concentration of ET, which parameter will be affected? Right, like Vmax will be affected because Vmax is a property of ET. So Vmax is decreasing. Now, this is a very interesting one that in uncompetitive we can see that Km is also decreasing, right? Now, like Km is decreasing means this means affinity is increasing. But how does it sound? Like inhibitor add kar diya, fir affinity is increasing. It sounds very strange, right? So what is happening here? So it is very interesting. Like I will write it down. Why Km is decreasing, or like you can rewrite is why affinity is increasing while we are adding like inhibitors, right? The concept is an uncompetitive inhibitor lowers the measured Vmax. Like if I am measuring the Vmax 1 before adding the inhibitor, the Vmax 2 will be lower than Vmax 1, right? So whenever an uncompetitive inhibitor is added, it lowers the measured Vmax. So apparently the Km also decreases because the substrate concentration required to reach 1/2 of the Vmax decreases also. And by what factor? Alpha dash. Let me write down what I just said, that since this is the V max 1 and this is the V max 2, since there is a decrease in V max 2, less amount of substrate is needed to reach the Vmax 2, right? Since the like upper limit is already decreasing, so I need less substrate concentration to reach the Vmax. Since the substrate concentration is decreasing, apparently the Km is also decreasing. The affinity is not increasing at all, but apparently the substrate required to reach 1/2 of the Vmax decreases. So that is why Km is decreasing. We cannot like increase the affinity of an enzyme towards the substrate by just giving uncompetitive inhibitor. No, it is apparently decreasing because less amount of substrate concentration is needed to reach Vmax by 2. Okay, but if what factor it is decreasing? This factor is nothing but our old friend alpha dash. Okay, so this is the factor by which Km is decreasing, and that is why Km apparent is equal to Km divided by alpha dash. Okay, this is the like juicy part of enzyme kinematics. Why Km is like decreasing and affinity is increasing? No, affinity is not increasing. It is apparently increasing because the Vmax is decreasing and substrate required to reach Vmax by 2 is less. Okay. So in uncompetitive there is another concept that inhibitor must bind with the another side of the enzyme, right? Another side of the enzyme, such way that the enzyme, like, only the catalytic activity is affected, not the substrate binding efficiency. What it means is that in ES condition, it is binding to the enzymes in such a condition that the catalysis where E will act on AS and the activation energy will decrease, and from the product this property of enzyme will be affected, but the binding of enzyme with substrate will not be affected, right? So inhibitor has to bind in the perfect area, so that the catalytic property is affected but not the binding efficiency of the enzyme with the substrate. So it is actually more significant for multi-substrate enzymes. Okay, so not for one substrate enzyme. So uncompetitive is very 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 rare kind of inhibition, reversible inhibition, very rare, and it is mainly significant in multi substrate enzymes. Okay. Okay, so now let's start with the mixed one. And in mixed, as I told you that, okay, so again in mixed one, mixed is nothing but the competition of combination of competitive and uncompetitive, and we can see that in uncompetitive situations the total pool of enzyme is decreasing. So again ET is decreasing, so Pmax is decreasing, no surprise. And Km, I told you that competitive will try to increase the Km and uncompetitive will try to decrease the Km. So Km has three fates in this. If both of them are you can think that competitive is pulling the Km upwards and uncompetitive is pulling the Km downwards. So if both the forces are equal, so then Km will be constant. If the competitive pull, competitive inhibition is trying to pull the Km to upper higher values. So if alpha is greater than alpha dash, that is the effect of competitive inhibition is greater than uncompetitive inhibition in unmixed inhibition, then the Km will increase, and the reverse is same. If uncompetitive downwards pull, I will say, not biologically correct, but I'm just giving a visual. So this is the Km, and competitive is trying to take it to a higher value, and competitive is trying to take it to a lower value. If both of these forces are equal, the Km will be constant. If this force is greater, the Km value will increase. If this force is lower, the Km value will decrease. A simple thing. Okay. So Km has three fates, that it can decrease, increase, and also remain constant. Okay. So in such condition where the pool is same, or the alpha and alpha dash is same, this condition is known as non-competitive. This is a special kind of mixed inhibition where alpha is alpha dash is same, and it is known as mixed non-competitive inhibition. And this non-competitive inhibition, interestingly, is the kinetics of irreversible inhibitors. Okay, resembles in the kinetics of irreversible inhibitors resembles this non-competitive pattern, kinetics of reversible inhibitor resembles this. Okay. Okay, and I think we are almost done with this discussion of enzyme. And is there anything in the next slide? Oh yeah, there are plots. Okay, so I will just give a short brief interesting point that why is it important to learn all this competitive, uncompetitive, and mixed. Where do we actually use it? So suppose you are designing a drug, and there are two situations given to you. That one situation is you need to increase the substrate concentration. Okay, so this is not a part of mathematics for biologists maybe, but I will just touch the concept and leave it here. So, and another condition is that you have to increase the pool of product. Okay, so you are designing a drug, so you have to think drug kaise kam karega, do I need to choose competitive inhibitor or do I need to use non-competitive inhibitor? The thing is that like whenever you are like want to increase the substrate concentration, then you can like choose competitive or non-competitive. It is not a issue. Why? Because in both cases, the in competition, so in competition there will like more substrate is required to reach the Vmax, so there will be like substrate accumulation. Okay, so like you can think it differently, like inhibitor is binding with the enzyme and product is not forming, so there will be more pool of substrate, like the substrate is utilization is decreasing overall, so there will be more pool of substrate, so you can increase the substrate concentration. So you can use like competitive or non-competitive inhibition, but if you want to increase the concentration of the product, it must be non-competitive, must be non-competitive. Competitive. Why it must be non-competitive? Okay, this is beyond the scope of discussion, but quickly if I say that for non-competitive, you can see that when like the substrate is increasing again, when the substrate is increasing, some of the substrate can actually, okay, so for competitive inhibition, we all know that when the substrate concentration is increased to a very high value, the effect of inhibitor is decreased completely. Okay, so what is the value, like what is the significance of alpha here? So for competitive inhibition, you can see that Km by alpha value, Km by Vmax value, here I will write that Km by Vmax apparent equal to Km by Vmax. What is the like what is the relation? There will be one alpha. What is this alpha represent? This is the like alpha is the factor by which the like concentration of substrate needs to be increased so that the inhibitor effect is gone. Okay, that is the like true meaning of alpha. So what is alpha? Even this same concept will be like applied in the Lotka-Volterra model. This is the like beauty of the science. If you understand one concept and you can like apply to a totally different area. Okay, so alpha is the like factor by which the substrate concentration needs to be increased so that the effect of inhibitor is not seen at all. Okay, now if we increase the substrate concentration by alpha, the competitive inhibition, it becomes like totally not affected by inhibitors, right? Okay, so can we apply this same for uncompetitive? No. Why? Because see, Km apparent by Vmax apparent equal to, what is the Km of that uncompetitive? It is decreasing, right? So Km by alpha, sorry, Km by alpha dash and again Vmax by alpha dash, right? So these alpha dashes are cancelling. So the ratio of Km and Vmax does not change. So there is no alpha or alpha dash in this ratio. So there is no factor by which substrate concentration can be increased so that the effect of inhibitor is gone. And this makes sense, right? It is binding to the like ES. It is binding to the ES. So it is forming ESI. So like if you increase the substrate concentration, it will only increase the ES concentration, right? So there is no way by increasing substrate you can like wash off the effects of inhibitor. No, you cannot do that. And even mathematically there is no alpha factor by which you can like increase the substrate concentration, because Km by Vmax value is constant in uncompetitive. For non-competitive, what is happening is like for non-competitive, the Km remains constant, right? Km apparent is equal to Km. So Km by Vmax is Km apparent by Vmax. What is the Vmax? The Vmax is Vmax divided by alpha dash. So this becomes alpha dash Km by Vmax, right? So there is a factor. If you increase the substrate concentration by this factor, to some extent the reaction moves to a normalized value. But again, like the uncompetitive part kicks in the mixed also. So but if you like, you cannot completely aware of the effect of inhibitor in uncompetitive or non-competitive. Sorry, you cannot do it uncompetitive. You cannot like aware of the effect of inhibitor in non-competitive. Okay, but to some extent, like this is the alpha dash, to some extent you can like normalize the situation. So to some extent you can increase the concentration of the product by increasing the concentration of the substrate in only in non-competitive, right? Only in non-competitive you can do that. So whenever you want to increase the concentration of product, the drug must be non-competitive. Like, now I know that there may be many confusions in this area also, the last part mainly, but again this is not the part of mathematics or biology. Maybe some other time we'll do that. Okay, so the last part of this enzyme kinematics is the plot. So I will just quickly brush up with it because बहुत देर से चल रहा है भी ये enzyme kinematics. Michael's Mendel's plot. The y is the v and the x is the substrate concentration. And how is the plot? This is the plot. This is the Vmax and this is the like Vmax by 2 and this is Km. This is S. Okay. This is simple. And for Line-Weaver, the double reciprocal plot is also known as Line-Weaver-Bark plot. Okay, Line-Weaver-Bark plot. What is this? This is like this. So what is the value of y? Y is equal to 1 by v. And what is the value of x? X is equal to 1 by s. And what is the like value of m? M is km by Vmax, right? This is why it is important, km by Vmax. अभी एक्सप्लेन किया ना, km by Vmax competitive, uncompetitive और non competitive और mixed में. तो this is the like importance of slope. And what is the c? C is 1 by Vmax. ज़्यादा ही खराब लिख रहा हूँ क्या? 1 by Vmax. Okay. And for 3, that is AD-Hopstein plot. AD-Hopstein plot. Just see these things because it is like very relevant, like important from the exam standpoint of view. I will just shortly write the AD-Hopstein plot. 1 by V equal to Km into S by Km into S, no, Km plus S. Km plus S by Vmax into S, right? What is this equation? This is the nothing but reciprocal of the Michael-Mendel's constant. Okay, now if we just multiply Vmax on both sides, Vmax by V, I'll just change the ink so that it is very prominent. Vmax by V is equal to Vmax into Km plus concentration of X by Vmax into concentration of S. The Vmax will cancel out and the equation becomes like the Vmax is equal to V into Km plus V into substrate concentration of S by substrate concentration of S, right? And if we just like play with the values, then we will find that V is equal to minus Km V by substrate concentration plus Vmax, right? I think I am right. We will take this one there and V will be common. This is right. So for V it is Y, and then again this is M, and this is like X, and this is C. So you can just plot the graph. Since M, you can see that M is negative, so it will be a negative slope. And so this is the graph here, the negative slope, and like Y is V and X is V by substrate concentration, and the like Y intercept is Vmax. And like you can, this is the graph of AD-Hopstein. तो mostly यही पूछते हैं कि like graph दे देगा and you will have different y coordinate and x coordinate, and then they will ask like ये कौन सा graph है, AD-Hopstein या like Hans-Wolf or या Line-Weaver or something, or Dixon or anything. Okay, so the next one is, नाम ले लिया मैंने, Hans-Wolf, right? Hans-Wolf plot. Hans-Wolf plot में क्या होता है? Then again you start playing with Line-Weaver plot and you will finally end up with this. V equal to क्या था इसमें, एम was 1 by v max into s plus km by v max, right? So abhi this will be the y, this will be the m, this will be the x, and this will be the c. Okay, so the m is positive, and again the graph is like this only. So you can like find the, ऐसे नहीं होगा, ये होगा, हाँ, you can find the like, this is the y intercept, and then this is the y, this is the x, and you can just draw it on your own. तो हाउ टू, द मेन इशू इज दैट हाउ टू रिमेंबर, मतलब एडी हब्स में वाई क्या होगा और हेंसुल में वाई क्या होगा. जस्ट ऑलवेज फोकस ऑन द वाई. मैं क्या करता था कि लाइक ईवी व्हीकल अभी बहुत चल रहा है मार्केट में, तो इलेक्ट्रिक व्हीकल दैट इज ईवी. ईवी इज लाइक एडी हब्स टी एंड द वाई कोऑर्डिनेट विल बी वी. ओके, एंड एक्स में एक, मतलब एक्स और वाई में एक सबस्ट्रेट तो रहेगा ही. जस्ट रिमेंबर दैट सबस्ट्रेट विल बी ऑलवेज देयर. So if it is not in the y coordinate, it will be in the x coordinate, and if it is in the x coordinate तो y coordinate, it is in the y coordinate तो x coordinate में भी substrate रहेगा. तो if you can remember EV, then for AD Hubs T, y is equal to v, and x is equal to like v by s. You have to like brute force your brain to remember this one. And for Hansulf, क्या था, मतलब ऐसे ही like you have to find something interesting to remember this one. Okay, HSV or something like that, HSV or something like that, you have to like remember that one. So these are the two, the four graphs, four plots, and another one is like Dixon plot. Dixon plot you will not find this in like void and void में नहीं मिलेगा, लेंजन में नहीं मिलेगा. टी पामर का बुक में इसका like जिक्र है इसमें. टी पामर इज अ ओल्ड बुक, तो इसमें थोड़ा जिक्र है इसका. तो इट इज ऑल्सो जस्ट नो दैट इट इज ऑल्सो नोन एज डिक्सन. ओके, डिक्सन प्लॉट. रेयरली क्वेश्चंस आर आस्क्ड बिटवीन दिस, बट इन दिस, बट मतलब लेबोरेटरी में और वो इनहिबिशन स्टडीज़ में ना बहुत काम आता है ये. बिकॉज एज आई टोल्ड यू, मैक्सिमम रिसर्च पेपर्स आर लाइक बेस्ड ऑन इनहिबिशन, एंड काइनेटिक स्टडी इज लाइक of newly discovered drugs are very important, so you have to study this one. Okay, and what is the Dixon plot? It is a graph between 1 by v and concentration of I. Now we will say that I का concentration तो नहीं है इसमें, like line Weber Burke plot में, double reciprocal plot में, तो वो I का concept नहीं है. तो आई का कॉन्सेप्ट कहाँ से आएगा? इट विल कम फ्रॉम द अल्फा. तो यू कैन अंडरस्टैंड दैट इफ यू वांट टू ब्रिंग अल्फा इनटू डबल रेसिप्रोकल प्लॉट, यू नीड टू कंसिडर द लाइक inhibitions, right? There are three kinds of inhibitions: competitive inhibition, uncompetitive inhibition, and like non-competitive, or you can say it is four types, like mixed inhibition. Okay, so ये चारों के लिए इसका ग्राफ अलग होता है, and it has different like y intercept and slope and everything. तो यहाँ मैंने एक टेबल दे दिया है. इफ समवन इज इंटरेस्टेड, यू कैन सी दैट like for competitive this is the like intersection of two or more values of s, and this is the slope. For non-competitive, this is the slope. For uncompetitive, this is the slope, and like flattened, yeah, for mixed, and this is the slope. Okay, so you can just you can also visit this website if you're really interested into Dixon plot. So you can just dive in, like there is an article, and I have just taken this photo from that article only. This is the like DOI, so go there and see if you're interested in Dixon plot. For now, just remember that Dixon plot is also known as the secondary plot of inhibition. Secondary plot of inhibition. Okay, ये याद रखो फिर. And then और क्या है? Okay, I will show another one actually. This is important, I think. Okay, I'll just isolate this part and I will show you something. Okay, so so for competitive inhibition, the Km apparent is alpha Km, right? The Km apparent is alpha Km. Okay, and what is alpha? The value of alpha is 1 plus concentration of I by KI into KM, तो कर लो, KM डैश लिख रहा हूँ मैं, अभी अपरेंट KI लिखूँगा, तो मल्टीप्लाई दिस KM प्लस KM into concentration of I by KI हो गया. So now again you can see that this is like Y and this part is M and this I is X and this is C and M is like क्या है मतलब M is positive, so what will be the graph? This will be the graph and ये हो जाएगा KM, right? This is the C, this is the C and like y will be this one and x will be I, x का ये I हो जाएगा and just put y equal to 0 and you will find x, right? That is the this one. क्या होगा मतलब x if this is 0 तो ये सर आ जाएगा and minus ki I think. Let's solve it, no? Let's solve it without like wasting much time. So this will be 0 equal to km plus km into I by ki. So this will come this side and this will get cancelled. So I मतलब x equal to minus ki हो जाएगा. तो this intercept is minus ki. Okay. Just remember this graph also. मतलब सवाल देखा है मैंने कुछ competitive exams में, ये ग्राफ दे देगा and it will be like it will be like km dash and this will be like inhibitor, don't like abhi they will ask this or something like this or the slope or something like that. Don't get confused. So you can just in the exam hall also you can derive it from here only. So you don't remember all of these things, but remember Eddie Hofstee and remember Hans Wolf plot and also remember the Dixon plot. It is also known as secondary plot. Remember Dixon plot matlab the most in like the best question that I have seen in Dixon plot is the किसके versus किसका है, मतलब what is the y and the x coordinate of Dixon plot, because that is the only thing that is like staying constant, right? Throughout all these inhibitions, and you can see the values. It is like next to impossible for any like student to remember all these things, all the slopes and the y intercepts and everything. तो Dixon plot से ये तो नहीं आएगा कभी. तो and if you are also like a PhD guy who needs Dixon plot software है तो उसमें डाल दो, सब concentration आ जाएगा. You don't have to like sit and numerically solve the Dixon plot nowadays. So it is like irrelevant to discuss all like these things in Dixon plot only. So remember the Dixon plot is secondary plot of inhibition and it is like between 1 by V and I. Okay. And also remember that K apparent is alpha Km for competitive inhibition and इसमें ऐसा कुछ ग्राफ दे देगा and maybe they will just ask you that ऐसा ग्राफ हो रहा है and this is the y and x coordinate, तो ये कौन सा inhibition है, CI या non-competitive or non-competitive. Or you can also like play around with it and like find the graphs of non-competitive and non-competitive, right? Okay. So I think that we are done with enzyme kinematics. बहुत लंबा चल गया ये, चलो सही है. Like as I said, we should like spend a day on this. Okay, so enzyme kinematics is done. Let's take a deep breath, and dilution problem is the last topic of today and it is really simple though. Okay, so dilution problem. Process of what is the like definition of dilution? That is process of reducing the concentration of solute in a solution. Like concentration of solute will decrease in the solution. How it will decrease? By adding the solvent. The basic definition of dilution is this: process of reducing the concentration of solute in a solution by adding more of solvent, right? So एक ही टाइप का आता है इसमें सवाल, C1 V1 equals C2 V2 वाला. तो what is C1? C1 is the concentration, and what is C2? C2 is like the concentration of the second solute. So I'll just draw some box like this and maybe like this. हो गया. तो क्वेश्चन क्या आता है? क्वेश्चन आता है like this is the stock solution. क्वेश्चन मतलब लैब में भी यही करना होता है. This is the stock solution and this is the final solution that you need for some random ABCD experiment. And इसमें क्या है भी मतलब this was concentration C1 and you have to take some volume V1 so that ultimately ये volume का ये concentration का सॉल्यूशन बन जाए. तो लाइक rather than hypothesizing anything, let's dive into a question and discuss it. Okay, तो फिर क्लियर हो जाएगा. आई नो लाइक लॉट ऑफ पीपल फेस प्रॉब्लम इन दिस ऑल्सो, पर अभी ये क्लियर हो जाएगा. इट इज रियली सिंपल. ओके ओके. सो हियर यू हैव अ स्टॉक सॉल्यूशन ऑफ HCl. सबका फेवरेट एसिड यही होता है, हर क्वेश्चन में HCl ही रहता है बस. यू हैव अ स्टॉक सॉल्यूशन ऑफ HCl with a concentration of 6 molar, right? 6 molar. तो लिख लो that you have a like इसी कॉन्सेप्ट को अगर ले लाओ, मतलब ले आओ इस स्लाइड में, तो दिस इज द लाइक स्टॉक एंड दिस इज फाइनल. सो दिस इज स्टॉक सॉल्यूशन, दिस इज फाइनल सॉल्यूशन, एंड इन दिस HCl का है दोनों में, एंड द कंसंट्रेशन इज इन द स्टॉक सॉल्यूशन इज दिया हुआ है कि दिस इज स्टॉक सॉल्यूशन, कंसंट्रेशन 6. तो इसमें C1 there is a concentration is 6 molar. तो अभी तो like you are pro about like what is molar or non polar, तो इसका तो ज़रूरत नहीं है अभी. 6 molar you needed to prepare 500 ml of diluted solution. needed to prepare मतलब फाइनल में ये होना चाहिए 500 ml, राइट. फाइनल में ये चाहिए मुझे, ठीक है. तो 500 ml of diluted solution. तो diluted solution, this is the final solution, not the stock solution. Okay, with a concentration of like 2 molar. तो that is the final concentration, this is the final volume. तो अभी क्या ही पूछेगा, और V1 ही पूछेगा इसमें. तो how much is the stock solution, how much stock solution मतलब V1. V1 पूछना मतलब बोलना है तुम्हें. should we use, सिंपल फंडा है, C1 V1 इक्वल टू C2 V2. एक ही बात है, लाइक द नंबर ऑफ मोल्स विल बी कंजर्व्ड. ओके, सो C1 V1 इक्वल टू C2 V2. इसमें दो क्वेश्चन है आई थिंक. हाउ मच स्टॉक सॉल्यूशन शुड यू यूज, एंड दिस इज लाइक नंबर 1 क्वेश्चन. नंबर 2 क्वेश्चन इज हाउ मच सॉल्वेंट यूजुअली वाटर शुड यू ऐड. द बेसिक थिंग ना, मतलब तुम लेकर कैसे डाइल्यूशन करोगे. दिस इज व्हाई आई गिव द डेफिनेशन ऑफ डाइल्यूशन, दैट फॉर डाइल्यूशन क्या कर रहे हो, बाय एडिंग मोर सॉल्वेंट, राइट. तो यही है क्वेश्चन में कि हाउ मच सॉल्वेंट चाहिए तुम्हें. तो फिर प्लग इन द लाइक बेसिक थिंग्स, दैट इज 6 into V1 इक्वल टू C2 मतलब 2 into 500 ml. You just don't need to convert the like 500 ml into liter, because तुम्हारा V1 भी 500 ml मतलब ml में ही आएगा, तो that is not an issue. इसको 3 बोल दो. V1 इक्वल टू 500/3 ml. इसका कितना होता है, यही होगा और क्या होगा, मतलब 7 कर लो इसका ml. तो दिस इज लाइक 167 ही कर लो मतलब ml. ओके, अप्रोक्सीमेटली 167 ml. सो द आंसर ऑफ 1 इज यू नीड अ वॉल्यूम ऑफ 167 ml फ्रॉम द स्टॉक सोल्यूशन. ओके, तो अभी द फाइनल वॉल्यूम इज 500. तुमने V1 कितना लिया स्टॉक सॉल्यूशन को, 167. तो बाकी का मतलब 500 में से 167 तो V1 से आ गया, बाकी का कहाँ से आएगा, सॉल्वेंट से ही आएगा ऑब्वियसली. एंड वही पूछा है मतलब हाउ मच सॉल्वेंट ऐड करना होगा. तो हाउ मच सॉल्वेंट इट इज़, इसको मतलब सब्सट्रैक्ट कर दो. सब्सट्रैक्ट करने से कितना आता है, 333 ml. तो हाउ मच दिस इज द सॉल्यूशन ऑफ द 2, हाउ मच सॉल्वेंट इज नीडेड, 333 ml of solvent is needed. Okay, this is like really simple. I think this is done and this makes complete sense. I think this is not confusing at all, right? C1 दिया हुआ था, C2 भी था, V2 भी था, V1 निकलना था, and the formula is C1 V1 equal to C2 V2. Why C1 V1 is equal to C2 V2 वो भी मतलब समझा दिया मैंने बैक में, क्योंकि नंबर ऑफ मॉलिक्यूल शुड बी सेम. एंड मतलब इसको तो मैं C1 V1 C2 V2 प्रॉब्लम ही बुलाता हूँ, मतलब डाइल्यूशन प्रॉब्लम. ये देखो यहाँ पर भी दिया हुआ है C1 V1 C2 V2 इक्वेशन एंड एवरीथिंग. ओके, तो वॉल्यूम निकल गया V1 का, V2 मतलब दैट इज द फाइनल वॉल्यूम. तो यू कैन ऑल्सो राइट इट लाइक दिस, लाइक V final इज इक्वल टू 500, V इनिशियल इज इक्वल टू 165. तो कितना सॉल्वेंट ऐड किया, तो ऑब्वियसली विद सब्सट्रैक्ट ना, बाकी का वॉल्यूम कहाँ से आया. इट कैन नॉट लाइक अपीयर मैजिकली, यू हैव टू ऐड समथिंग. एंड again go back to the basic definition, what do you add, by addition of more solvent. तो solvent ऐड कर रहे हो, फिर find the solvent. तो हो गया 500 minus 167, that is like कितना हुआ 333. ओके, आई थिंक और तो कुछ नहीं, आज का यही था। तो कोई कन्फ्यूजन, कोई क्वेश्चन, कुछ क्वेरी है तो मेरा तो लिंक्डइन पे प्रोफाइल का लिंक दिया ही हुआ है, जस्ट पूछ लो मुझसे, कनेक्ट विथ मी, टॉक टू मी, एंड वंस यू कनेक्ट विथ मी यू कैन ऑल्सो कनेक्ट विथ माई नेटवर्क। तो कर लो कनेक्ट, आ जाओ लिंक्डइन में, बात करते हैं और क्या। और कोई कन्फ्यूजन है तो यू कैन लाइक डीएम मी, बोल दो कि मैंने मेल किया है आपको, एक बार देख लेना, तो आई विल जस्ट लुक इनटू इट एंड गिव यू द सॉल्यूशन। ओके, दिस इंटरेक्शन लाइक शुडंट बी लाइक मतलब ये वेबिनार हो गया एंड द इंटरेक्शन इज आउट, आई डोंट वांट दैट फ्रॉम माई स्टूडेंट्स और एनीवन। तो इंटरेक्शन तो बनना चाहिए भाई, कनेक्शन तो होना चाहिए। तो आ जाओ सब लिंक्डइन पे, मिलते हैं फिर डे 2 वेबिनार में। ओके, चलो बाय।